Hello there, and welcome to Midnight Geography. Tonight, we'll drift into the geological story of America, where stone remembers what air forgets. Geology is the planet's autobiography, written in layers. It speaks in the language of pressure and time, revealing its narrative through the slow poetry of uplift and erosion. What appears solid is actually fluid when measured across millennia. Mountains rise like breathing, valleys deepen like sighs, and every rock face holds memory of ancient seas, volcanic fury, or the patient work of ice. If you enjoy these peaceful geographical explorations, consider liking and subscribing. It helps other curious minds find their way here too. But for now, let's begin. The Burgess Shale reaches across the border from Canada into Montana's Glacier National Park, where it preserves a moment of ancient ocean life with startling intimacy. 508 million years ago, soft-bodied creatures drifted through warm seas, their delicate forms normally destined to vanish without trace. But here, in fine-grained mudstone, they were buried so quickly and so gently that even their digestive systems remain visible. Scientists examining these fossils can trace the outline of internal organs, see the structure of primitive eyes, observe the arrangement of feeding appendages. The mud became stone. The stone became archive. And now these fragments of the Cambrian explosion rest in mountain valleys, waiting for patient hands to reveal what the ocean floor once held. In California's Death Valley, exposed rocks speak of an Earth almost unrecognizable to modern eyes. 1.8 billion years old, these ancient stones formed when the planet was barely half its current age. No complex life existed yet. Only single-celled organisms drifted through seas that covered landscapes not yet assembled into familiar continents. These rocks witnessed the slow gathering of land masses into their first supercontinent, saw atmospheres transform, watched as oxygen gradually accumulated to levels that would eventually permit more elaborate forms of life. They are among the oldest exposed surfaces in North America, windows into an Earth so ancient it belongs more to geology than to biology. Stand before them, and you stand before deep time made tangible, before stone that predates nearly everything we think of as life's story. The New Madrid seismic zone lies buried beneath the seemingly stable heartland of Missouri, a geological fault system that occasionally reminds the surface world of the restless forces below. In 1811 and 1812, 3 massive earthquakes struck in quick succession, each powerful enough to ring church bells in Boston, over 1,000 miles distant. Eyewitnesses reported the Mississippi River flowing backward as the land heaved and settled, as bluffs collapsed and sandbars emerged where none had been. The shaking created temporary waterfalls, changed the course of streams, formed new lakes and sunken land. These weren't tremors from the active plate boundaries that define the West Coast. These came from ancient weaknesses in the continental interior, fault lines formed hundreds of millions of years ago that still occasionally slip, still occasionally remind us that no ground is truly stable, that all Earth remains subject to forces operating on timescales beyond human reckoning. Arizona's petrified forest contains trees that have forgotten how to be wood. 225 million years ago, towering conifers fell in ancient floodplains, were buried quickly in volcanic ash and river sediment. And then, molecule by molecule, silica-rich water moved through the buried trunks, replacing wood cells with quartz crystal. The replacement was so exact, so precise, that growth rings remain visible, that the cellular structure of ancient wood persists in stone. Now these fossilized giants lie scattered across badlands, some still resembling fallen logs, others fractured into segments, all of them transformed into rainbows of mineral color, reds and purples and yellows where different trace elements stain the quartz. Each one weighs several tons. Each one was once alive, photosynthesizing under Triassic skies, long before the first dinosaurs walked beneath their branches. The Columbia River basalt flows stretch across Washington and Oregon in layer upon layer of black stone, the remnant of the largest known lava floods in Earth's history. Imagine not a single volcano erupting, but rather the Earth splitting open along great fissures, with molten rock simply pouring forth like water from a broken pipe. This happened repeatedly between 17 and 6 million years ago, each eruption flooding the landscape with basalt that spread for hundreds of miles before cooling. The flows stacked upon each other, 10, 20, sometimes more than 100 separate lava floods frozen one atop another, until in some places the accumulated basalt reached depths of 6,000 feet. Rivers have since carved canyons through these layers, revealing the striped history of repeated inundations, each dark band representing a separate moment when the earth opened and the interior poured forth, reshaping the surface world with patient, molten insistence. Kentucky's Mammoth Cave system extends through limestone darkness for over 400 miles of mapped passages, making it the longest known cave system on Earth. And yet new chambers continue to be discovered, new connections made between previously separate sections. The limestone itself was deposited as an ancient seabed, layer upon layer of compressed marine organisms accumulating over millions of years. Then, as the land rose and rivers found new courses, slightly acidic groundwater began its slow work of dissolution. Carbon dioxide mixing with rainwater created a weak acid that, drop by drop, year by year, dissolved pathways through the stone. 10 million years of patient water chemistry carved these passages, widened these chambers, created underground rivers that still flow in darkness. The cave grows still, imperceptibly, as water continues its gentle erosion, as new cracks become new passages, as the darkness beneath Kentucky slowly expands into territories no light has ever touched. The channeled scablands of eastern Washington wear the scars of catastrophe-made landscape. Here, the earth was carved not by patient rivers working over millions of years, but by water unleashed in a geological instant. 15,000 years ago, glacial Lake Missoula, a vast inland sea trapped behind an ice dam in Montana, suddenly broke free. The ice dam failed, and water equivalent to all the world's rivers flowing for 2 weeks surged across eastern Washington in a matter of days. The flood moved at highway speeds, carrying house-sized boulders, scouring bedrock down to fresh stone, creating waterfalls that have since vanished, carving channels through solid basalt. What remains is a landscape unlike any other. Bare rock, scoured clean, isolated buttes standing as remnants of what the flood didn't reach, dry waterfalls hundreds of feet high, giant ripples in gravel bars that resemble sand ripples, but measured at the scale of buildings. The land remembers violence, but the violence is long past, leaving only these strange geometries etched in stone. Florida rests upon a platform of limestone 2,000 feet thick, a foundation built entirely from the compressed remains of ancient sea life. For 150 million years, this land was submerged beneath warm, shallow seas, where coral reefs flourished and shellfish multiplied in countless billions. As these organisms died, their calcium carbonate shells and skeletons drifted down, accumulated on the seafloor, compressed under their own weight into stone. The entire peninsula is essentially a vast graveyard, a monument constructed from marine life stacked so deep that it forms the substrate for everything above. Even now, the limestone continues its slow work of dissolution, creating sinkholes where acidic rainwater eats through the rock, forming the springs and caves that honeycomb the state's underground. Florida appears solid, but beneath the surface, water moves through passages carved in ancient shells, through stone that was once alive, through a landscape that is as much liquid as solid. The San Andreas Fault has been pulling California apart and pushing it northward for millions of years, moving Los Angeles steadily along a path that has carried it 250 miles from its original position. The movement continues still, at roughly the same rate your fingernails grow, slow enough to seem static in human time, fast enough to reshape entire landscapes across geological ages. Stand on one side of the fault, and you stand on the Pacific Plate, being dragged northwest. Stand on the other, and you rest upon the North American Plate, relatively stationary. The two sides grind past each other, sometimes smoothly in slow creep, sometimes in sudden violent jerks that we experience as earthquakes. Eventually, millions of years from now, Los Angeles will arrive at the latitude of San Francisco. And still, the plates will continue their patient journey, driven by convection currents in the mantle below, by forces so vast and so persistent that they treat mountain ranges as temporary obstacles. Minnesota's Morton Gneiss emerges along the Minnesota River Valley, exposing rock 3.5 billion years old, among the oldest stone at Earth's surface. This rock formed when the planet was barely cooled from its molten infancy, when the first stable crust was just beginning to solidify and persist. The continents as we know them did not yet exist. The atmosphere would have been poisonous to modern life. And yet here, this rock was forming, crystallizing from magma, beginning its long journey through geological time. It has been buried and uplifted, heated and compressed, transformed from its original igneous form into metamorphic gneiss with distinctive banding. It has witnessed nearly 80% of Earth's entire history, sitting silent through the origin of life, through the oxygenation of the atmosphere, through the assembly and breakup of multiple supercontinents, through ice ages and warming periods, through extinctions and radiations, until finally erosion exposed it here in this valley, where we can place our hands upon stone that formed when Earth was young. The great unconformity at the Grand Canyon represents time made visible through its absence. Here, rocks from different eras sit directly against each other, with 1.2 billion years of history simply missing between them. Below lies ancient metamorphic rock. Above sits younger sedimentary layers, but the entire span between them has been eroded away, carried off by ancient rivers and winds and seas that left no trace beyond this gap in the record. Stand at the boundary, and you place one hand in time before complex life existed, the other in an age of shallow seas and primitive organisms. Between your hands stretches a void, a silence in stone, an entire chapter of planetary history that occurred but left no local record. The unconformity reminds us that geology is as much about absence as presence, that what's missing from the rocks often tells as much story as what remains, that deep time includes not just accumulation, but removal, not just deposition, but erosion. Georgia's Stone Mountain rises 825 feet above the surrounding landscape, a massive dome of granite exposed by patient erosion. 300 million years ago, magma pushed upward from deep below, but never broke through to the surface. Instead, it cooled slowly underground, forming a vast pluton of coarse-grained granite. Then, over immense spans of time, the softer rocks that once covered this granite wore away, were carried off by wind and water, until finally the resistant granite itself was exposed. What we see now is essentially the root of an ancient mountain system, the buried core now revealed, standing against the sky in a dome shape created by exfoliation, the tendency of granite to shed curved sheets of rock as it expands slightly when the weight of overlying rock is removed. The mountain continues this slow process of shedding, releasing thin shells of stone that peel away like layers of an onion, each one representing another moment in the mountain's gradual unmaking. The Yellowstone supervolcano beneath Wyoming holds a magma chamber 55 miles long, fed by a deep mantle plume that has remained relatively stationary while the North American continent drifts southwest above it. This creates a distinctive pattern visible in the landscape, a chain of progressively older volcanic calderas stretching across the Snake River Plain, each marking a moment when the hotspot broke through and erupted catastrophically. Yellowstone itself has erupted 3 times in the past 2 million years, each explosion ejecting hundreds of cubic miles of rock and ash, each creating a caldera that later partially filled with new volcanic material. The system erupts approximately every 600,000 years. The last eruption occurred 640,000 years ago. Simple arithmetic suggests another eruption is due, though due in geological terms offers little precision. The next eruption could occur tomorrow or 50,000 years from now. Meanwhile, the magma chamber pulses and breathes, pushing the land upward, creating the hot springs and geysers that make Yellowstone distinctive, reminding us that beneath our feet, the earth remains molten, patient, and occasionally catastrophic. Oklahoma has become one of the most seismically active regions in America, surpassing even California in the frequency of measurable earthquakes. In 2015 alone, over 900 tremors of magnitude 3.0 or greater shook the state, a dramatic increase from historical patterns. The earthquakes are not natural in origin, but rather induced by human activity, specifically by the injection of wastewater from oil and gas operations deep underground. The high-pressure fluids migrate into faults that had remained stable for thousands of years, lubricating them, reducing friction, allowing them to slip. What emerges is an accidental geological experiment demonstrating how even stable continental interiors can be made to shake, how faults that seemed dormant can be reawakened, how the boundary between natural and human-caused geological processes grows increasingly blurred as our industrial activities reach deeper into the Earth's crust and inadvertently trigger forces that normally operate on geological timescales. The Bingham Canyon mine in Utah represents the largest human excavation on Earth, a pit so vast it's visible from space, so deep that its walls descend in terraced rings like an inverted zipper. More than 6 billion tons of material have been removed since mining began in 1906, creating a void nearly 4,000 feet deep and 2.5 miles wide. The extraction of so much mass has measurably affected the local gravitational field. Sensitive instruments can detect the gravitational anomaly where mountain once stood, and now only absence remains. The mine produces copper, gold, silver, and molybdenum from ore that formed when mineral-rich fluids moved through fractured rock tens of millions of years ago, concentrating metals that had been dispersed throughout the crust. What took geological ages to concentrate, industrial activity disperses in decades. The pit grows deeper still, its walls stepping down in careful increments, each terrace representing a level of excavation, the entire structure a monument to human appetite for metal and our willingness to remake landscapes in service of that appetite. New York's Adirondack Mountains present a geological paradox. They are actually rising faster than erosion wears them down, growing roughly 2 millimeters per year as deep forces push them upward. Most ancient mountain ranges are in decline, being gradually reduced by wind and water. But the Adirondacks demonstrate that uplift can persist long after the collisions that created them have ceased. The mountains themselves are old, their rocks dating back over 1 billion years, but the uplift is relatively recent in geological terms, driven by a hot spot in the mantle below or by isostatic rebound as the crust adjusts to the removal of overlying material. The result is a landscape that appears ancient but is actually dynamic, where streams cut down through rock even as the rock rises beneath them, where elevation increases imperceptibly but measurably year by year. Stand in the Adirondacks, and you stand on ground that is rising, that refuses to submit entirely to gravity's patient work, that maintains its height through processes operating far below the surface, in the hot, plastic layers of the mantle where rock flows like thick fluid across timescales that reduce human history to a brief flicker. The Carrizo Plain in California offers the clearest visible evidence of San Andreas fault movement anywhere along its length. Here, away from coastal development, the fault cuts across flat terrain in a nearly straight line, creating distinctive topography that reveals its character. Offset stream channels show where the fault has shifted. A creek that once flowed straight across now bends sharply where the two sides of the fault have moved laterally past each other. Fence lines installed before the great 1857 earthquake remain offset by 30 feet, marking the amount of displacement in that single event. The plain preserves this evidence because erosion and development haven't obscured it, because the landscape remains open enough that the fault's signature stands clear. Walk along the fault, line here, and you can see exactly where the Pacific Plate meets the North American Plate, where two pieces of continent slide past each other at the pace of growing fingernails, occasionally sticking and then lurching forward in the earthquakes that have shaped California's geological and human history. Wisconsin's Baraboo quartzite tells a story of transformation spanning nearly 2 billion years. The rock began as sand on ancient beaches, quartz grains worn from even older mountains, deposited in horizontal layers by waves and currents. Then burial. Miles of sediment accumulated above, pressing down with immense weight. Heat and pressure transformed the loose sand into solid quartzite, fusing the grains until boundaries between them nearly disappeared. Then came the collision that built an ancient mountain range, forces so powerful they tilted the quartzite beds nearly vertical. And finally, after all this, burial, metamorphosis, tilting, came erosion, the removal of everything above, the exposure once again of rock that had been deeply buried. Now the Baraboo Hills rise as quartzite ridges oriented north-south, their hard stone resisting erosion while softer surrounding rocks wore away. Each ridge represents an ancient beach, turned to stone, tilted on edge, and revealed. The rock remembers being sand. The sand remembers being mountain. And the mountain was itself made from the erosion of still older peaks in an endless cycle of uplift and wearing down. The racetrack playa in Death Valley presents one of geology's most photogenic mysteries. Large rocks that leave long trails across the dry lakebed as if they had sailed across the mud on their own. For decades, no one witnessed the movement. The stones simply appeared in new positions, their tracks stretching behind them, sometimes straight, sometimes curved, occasionally intersecting. The explanation, discovered only recently through time-lapse photography and careful observation, involves a rare combination of conditions. On winter nights, when thin ice forms across the playa surface, morning sun begins to melt it. Gentle winds catch the floating ice sheets, which push against rocks embedded in the ice, sliding them across the slick mud beneath. The movement is slow, barely perceptible, requiring the perfect alignment of cold nights, thin ice, morning sun, and steady breeze. The rocks weigh hundreds of pounds but move nonetheless, their journeys recorded in trails that persist until the next rain smooths the playa surface. Mystery solved, but wonder undiminished, nature performing its slow choreography when no one watches. Pennsylvania sits atop one of the world's great coal deposits, beds of anthracite coal that represent ancient forests transformed by pressure into nearly pure carbon. 300 million years ago, during the Carboniferous period, literally named for its coal formation, vast swamp forests covered the region. Giant ferns and primitive trees grew, died, and fell into stagnant water where low oxygen levels prevented complete decay. Layer upon layer of plant material accumulated, bark, leaves, spores, wood, until the weight of accumulation became substantial. Then came the Appalachian mountain building event, with massive tectonic forces that not only uplifted the land, but applied heat and pressure to the buried plant layers. The pressure drove out water and volatile compounds, concentrating the carbon until what remained was anthracite, the hardest coal, burning hot and clean. The coal seams follow the folds of the Appalachians, bent and tilted by the same forces that raised the mountains, each seam representing an ancient forest floor, a moment of growth and burial, now compressed into black stone that burns with the condensed energy of carboniferous sunlight. The Cascadia subduction zone lies hidden beneath the Pacific waters off Washington, Oregon, and Northern California, a geological boundary where the Juan de Fuca plate slides beneath the North American plate at a rate of several centimeters per year. This is not a gentle process. The plates lock together, building stress over centuries, then release catastrophically in earthquakes of magnitude 9 or greater. The last such event occurred on January 26, 1700. We know the precise date because Japanese records documented the tsunami that arrived hours later, waves with no corresponding local earthquake, traveling across the Pacific from an American coast that had no written record of the disaster. The evidence appears in sand layers deposited by tsunamis, in drowned coastal forests, where trees still stand dead in saltwater marshes, in Native American oral histories speaking of the ground shaking and the ocean rising. The zone generates these massive earthquakes roughly every 500 years. 325 years have passed since the last one. The plates continue their patient grinding, stress accumulating in locked segments beneath the seafloor, waiting for the moment when friction fails and the ocean floor lurches upward, displacing water, sending waves toward shore. Devil's Tower rises 867 feet above the Wyoming plains, a nearly vertical column of igneous rock that seems to belong to a different landscape entirely. 50 million years ago, magma pushed upward toward the surface but never broke through, cooling instead into phonolite porphyry underground. As the molten rock solidified, it contracted, fracturing into hexagonal columns, the same geometric pattern that appears when mud dries and cracks, but here frozen in stone. Then came the slow work of erosion, the removal of all the softer sedimentary rock that once surrounded this intrusion, until only the hard, igneous core remained, standing isolated against the sky. The columnar structure gives the tower its distinctive fluted appearance, as if it were carved deliberately rather than revealed by time and weather. Native American legends speak of bears clawing at the rock, trying to reach people who had climbed to the top, and indeed, the vertical striations do resemble enormous claw marks. But the truth geology offers is equally wondrous. Stone that cooled in darkness now stands in light, a monument to patient erosion and the permanence of what resists wearing down. The Atchafalaya Basin in Louisiana represents the Mississippi River's preferred path to the Gulf of Mexico, a shorter, steeper route that the river continually attempts to follow. Rivers, given the choice, always seek the most efficient path downhill. The Mississippi currently flows past New Orleans in a course that is neither the shortest nor the steepest available. The Atchafalaya offers both. Without intervention, the Mississippi would abandon its current channel entirely, would shift its massive flow westward through the Atchafalaya, would leave New Orleans and Baton Rouge on the banks of a diminished backwater. This has not happened only because of the old river control structure, a massive engineering project completed in 1963 that regulates how much Mississippi water can enter the Atchafalaya, maintaining the current 70-30 split. It is one of the longest-running battles between human engineering and geological inevitability, a conflict that must be maintained constantly, or the river will claim its preferred path. The Atchafalaya Basin itself, cypress swamps, bayous, and wetlands, represents what the Mississippi wants to become, a more direct route that geology favors and that human infrastructure resists. Mono Lake sits in a volcanic basin east of the Sierra Nevada, a body of water so alkaline and saline that it supports almost no fish, but teems with brine shrimp and alkali flies. Beneath its surface rise tufa towers, fantastical limestone formations created where calcium-rich springs bubble up through the lakebed and react with the carbonate-rich lake water. The calcium carbonate precipitates immediately upon contact, building up over thousands of years into towers and spires and branching structures that resemble underwater cathedrals. When water levels dropped due to diversions feeding Los Angeles, many of these towers were exposed, standing now along the shoreline like alien architecture, their surfaces rough and porous, shaped by chemistry rather than intention. The lake itself is at least 760,000 years old, making it one of the oldest continuously existing lakes in North America. It has survived ice ages and drought periods, has risen and fallen, but persists in its volcanic basin, growing saltier as water evaporates and minerals concentrate, creating an environment so extreme that the organisms living there are found almost nowhere else, a reminder that life adapts to even the most challenging chemistry, finding ways to thrive in waters that would kill most creatures. The Homestake Mine in South Dakota eventually reached depths of 8,000 feet below the surface, becoming one of the deepest mines in the Western Hemisphere. At those depths, miners encountered rock temperatures exceeding 130 degrees Fahrenheit, heat rising from Earth's interior at a rate of roughly 75 degrees for every mile of descent. The mine required massive ventilation and cooling systems to remain operational, systems that fought against the natural geothermal gradient. But the heat itself tells a story about our planet's structure. The interior remains hot from the original heat of formation and from ongoing radioactive decay of elements like uranium and thorium. This heat drives convection in the mantle, which moves tectonic plates, which builds mountains and opens ocean basins. The Homestake Mine, in seeking gold, accidentally demonstrated one of geology's fundamental principles. We live on a thin, cool crust floating atop a hot, mobile interior. The mine is now closed to gold extraction, but has found new purpose as a physics laboratory, its deep, stable chambers providing ideal conditions for detecting subatomic particles. 8,000 feet of rock shields experiments from cosmic rays, turning a gold mine into a window on fundamental physics. Olympic National Park preserves beaches where tide pools have formed in rock that was once deep ocean floor. 35 million years ago, sediments accumulated on the Juan de Fuca Plate, far from any shore. Then, as the plate moved eastward and began subducting beneath North America, some of this deep-sea sediment was scraped off rather than carried down, a geological process called accretion, where the upper layers of an oceanic plate are added to the continental margin rather than destroyed. The scraped-off material was crumpled, folded, thrust upward, gradually building the Olympic Mountains from what had been seafloor. Now you can walk beaches where rock containing deep-sea fossils meets the surf, where stone that formed in darkness thousands of feet below the ocean surface has been lifted into daylight and stands against waves. The Olympics continue rising even now, pushed upward by the ongoing subduction offshore. Rain falling on these mountains, some of the highest rainfall in the continental United States, feeds temperate rainforests where moss drapes from trees growing on what was once ocean bottom, creating one of Earth's most distinctive convergences of geological processes and biological abundance. The Hayward Fault runs directly beneath the University of California, Berkeley campus, a segment of the San Andreas Fault system that presents its own distinct hazards to the Bay Area. Unlike some faults that move primarily during earthquakes, the Hayward Fault exhibits steady creep, continuous slow movement at a rate of about 5 millimeters per year. This creep is visible in the football stadium, where the structure is literally being pulled apart along the fault line, the gap widening millimeter by millimeter, year by year. Expansion joints installed during construction have been exceeded. The building now requires ongoing maintenance to address the separation. The creep releases some stress gradually, but not all of it. Geological evidence suggests the fault produces major earthquakes roughly every 140 years. The last significant rupture occurred in 1868. Simple arithmetic creates concern. Meanwhile, the stadium continues its slow split, a visible demonstration that the ground beneath the Bay Area remains in motion, that the boundary between tectonic plates runs not through remote wilderness, but beneath cities and universities, through the infrastructure of daily life, patient and persistent, and occasionally catastrophic. Malaspina Glacier in Alaska spreads across an area larger than Rhode Island, flowing down from the mountains and then spreading out across the coastal plain in a vast lobe of ice. The glacier moves so slowly that forests buried centuries ago remain preserved beneath it, trees still bearing marks where Ice Age mammals rubbed against their bark. The ice acts as a time capsule, protecting what it covers while simultaneously destroying the landscape through its grinding movement. Malaspina is what's called a Piedmont glacier, one that flows from mountain valleys onto flatter ground and spreads outward under its own weight like pancake batter on a griddle. The surface is covered with morainal debris, rock and soil scraped from valley walls and carried along, creating dark stripes and swirls visible from aircraft. Climate change is altering the glacier's balance between accumulation and melting, shifting the equilibrium that has maintained its size for thousands of years. But for now, it remains, a frozen remnant of the Pleistocene, flowing at the pace of meters per year, carrying its burden of rock and buried forest toward the sea, demonstrating how ice can shape landscape and preserve history simultaneously. The Permian Basin of West Texas and southeastern New Mexico holds layers of evaporate minerals, salt, gypsum, potash, deposited when a vast inland sea repeatedly filled and evaporated 250 million years ago. The region was then near the equator, in a climate of extreme heat and limited rainfall. Seawater would flood inland from the ancient ocean, creating a shallow sea. Then, isolated from the ocean by geological changes, the sea would evaporate under the intense sun. Minerals dissolved in the water would precipitate out in sequence as concentration increased. First calcium carbonate, then gypsum, finally salt. Then the cycle would repeat. Flooding, evaporation, mineral deposition, layer upon layer building up over millions of years. What remains is a stratigraphic record of these cycles, evaporate beds, hundreds of feet thick in places, interlayered with sediments from when the sea was open and marine organisms thrived. Now, the Permian Basin is known primarily for petroleum deposits, organic matter from those ancient seas, buried and transformed by heat and pressure into oil and gas. But the evaporates remain, silent testimony to an era when this now arid region repeatedly flooded and dried, when chemistry created stone from dissolved minerals. Crater Lake fills the caldera created 7,700 years ago, when Mount Mazama erupted and then collapsed, ejecting so much magma that the mountain's summit had nothing left to support it and fell inward, creating a bowl-shaped depression nearly 2,000 feet deep. The eruption was heard 1,000 miles away. Indigenous oral traditions from as far as the Great Basin preserve memories of the event, of mountain that exploded, of sky that darkened with ash. After the collapse, precipitation gradually filled the caldera, creating what is now the deepest lake in the United States at nearly 2,000 feet. The lake has no inlet streams and no outlet. Water enters only through rain and snowmelt, leaves only through evaporation and seepage. This creates remarkable clarity. The water is some of the purest on Earth, blue depths visible to extraordinary depths. Within the lake, Wizard Island rises as a volcanic cone that formed after the main collapse, built from smaller eruptions that occurred as the system settled. The caldera walls expose the internal structure of the volcano, layers of lava flows, ash deposits, each representing a separate eruption from the mountain's long history before its catastrophic end. And beneath the lake, geothermal vents still warm the deep water, reminding visitors that the volcanic system remains active, merely resting. The Appalachian Mountains once stood as tall as the Himalayas, thrust upward when continents collided 300 million years ago during the assembly of the supercontinent Pangaea. The collision crumpled rock layers, metamorphosed sediments into schist and gneiss, pushed what had been seafloor to elevations exceeding 20,000 feet. But that was their peak. Since then, for the entire span from the late Paleozoic to the present, erosion has been wearing them down. Wind and water, freeze and thaw, chemical weathering and physical breakdown, all working grain by grain to reduce the mountains. An estimated 3 to 5 miles of vertical rock has been removed, carried away by rivers to the Atlantic, deposited as coastal sediment. What remains are the roots of those ancient peaks, still dignified in their rounded summits, still commanding the landscape, but diminished from their original grandeur. The Appalachians teach patience and impermanence. Even mountains that rival the highest peaks on Earth eventually wear down, eventually soften into rolling hills, eventually become landscapes of gentle contours. Given enough time, erosion wins. Mountains are temporary features, moments of uplift in landscapes that trend toward flatness. The Badlands of South Dakota reveal 75 million years of geological history in horizontal layers stacked like pages in a book, each band of colored sediment representing a different chapter of environmental change. At the bottom lie dark shales from when the region was covered by the Western Interior Seaway, a vast, shallow sea that split North America in half during the Cretaceous period. Above that, lighter sediments from when the sea drained and rivers built floodplains across the emerging land. Higher still, volcanic ash layers from eruptions hundreds of miles away, ash that settled from the sky and became part of the sedimentary record. The bands of color, buff, tan, rust, purple, gray, reflect different mineral compositions and different source materials, creating the striped appearance that makes Badlands so visually distinctive. Erosion continues carving these sediments, creating a landscape of sharp pinnacles, deep gullies, and knife-edge ridges that shift and change with every heavy rain. What makes Badlands bad for agriculture? The lack of soil, the rapid erosion, the deeply dissected terrain makes them extraordinary for geology. The rock layers lie nearly horizontal and are easily read, a stratigraphic textbook written in sediment, revealing how North America transformed from seabed to swamp to grassland over spans of time measured in tens of millions of years. The Salton Sea in California formed accidentally in 1905 when irrigation canals from the Colorado River broke during flooding and water poured into the Salton Sink for 18 months before engineers could redirect the flow. The sink, a below sea level depression in the desert, rapidly filled, creating a vast lake where none had existed in modern times. But the formation was actually a repeat of natural cycles that had occurred many times before. The depression is the remnant of ancient Lake Cahuilla, which filled and evaporated repeatedly over hundreds of thousands of years as the Colorado River periodically changed course. Each time, the lake would fill, would become fresh and teeming with life, then would gradually evaporate, leaving behind salt flats. The current Salton Sea is now evaporating with no major inflow, growing saltier each year as water escapes to the atmosphere and leaves dissolved minerals behind. Fish introduced when the lake was fresher now struggle in increasingly saline conditions. The shoreline recedes, exposing lakebed dust that creates air quality problems. The Salton Sea is experiencing in decades what Lake Cahuilla experienced over centuries, the inevitable evaporation of water in a closed desert basin, a demonstration of geological processes we can watch in accelerated time. Ruby Falls in Tennessee descends 1,120 feet beneath Lookout Mountain to reach a waterfall 145 feet tall, flowing inside limestone caves dissolved over millions of years. The cave system formed as slightly acidic groundwater seeped through cracks in the limestone, gradually widening them, creating passages and chambers. The waterfall itself flows where an underground stream encounters a vertical shaft, plunging through darkness to a pool below before continuing its subterranean journey. The water that forms the falls enters through cracks far above, percolating down through the mountain, gathering in underground channels. It flows regardless of surface conditions. In drought or flood, summer or winter, the falls continue their hidden cascade. The caves containing Ruby Falls were actually discovered accidentally during excavation for a different project, their entrance having been sealed by rockfall centuries or millennia earlier. Now visitors descend by elevator and walk through passages adorned with stalactites and flowstone, formations created by mineral-rich water depositing calcium carbonate drop by drop over geological time. The waterfall represents the active process, erosion continuing, water still carving the mountain's interior, while the formations represent the slower process of deposition, of minerals coming out of solution, of stone building itself molecule by molecule in darkness. The mid-continent rift system cuts through Minnesota, Wisconsin, and Michigan, representing one of the greatest geological might-have-beens in North America's history. 1.1 billion years ago, the continent began to split apart. The crust stretched and thinned. Basaltic magma welled up from the mantle below. Lava flows spread across the landscape. For millions of years, the rift continued opening, creating a valley that might have become an ocean basin, that might have split North America into two separate land masses. But the rifting stopped. The forces driving it ceased or were overcome by other tectonic processes. The rift failed. What remains is a deep scar filled with dense basaltic rock, detectable now primarily through gravity measurements and seismic surveys. In some places, like Minnesota's North Shore, the ancient lava flows are exposed, tilted layers of basalt revealing the intensity of volcanic activity during the rift's active phase. Lake Superior occupies part of the Rift Valley, its great depth and elongated shape following the ancient zone of crustal weakness. The rift reminds us that not all geological processes reach their expected conclusion, that continents can begin to split and then change their minds, that the forces reshaping Earth's surface sometimes start projects they don't finish. Carlsbad Caverns in New Mexico extends through limestone in chambers so vast that the big room could hold 6 football fields, a space carved not by the usual process of slightly acidic rainwater, but by sulfuric acid rising from below. Deep beneath the Guadalupe Mountains, petroleum deposits release hydrogen sulfide gas. The gas migrates upward through rock layers, encounters oxygen-rich groundwater, and oxidizes into sulfuric acid, a much stronger acid than the carbonic acid formed from rainwater. This sulfuric acid dissolved the limestone rapidly, creating the enormous chambers and passages that characterize Carlsbad. The cave system extends both horizontally and vertically through the mountain, with passages at multiple levels representing different episodes of cave formation as the water table dropped over time. Where water still seeps through from above, traditional cave formations develop, stalactites hanging from ceilings, stalagmites rising from floors, columns where the two meet. But the scale of the main chambers reveals their unusual origin, spaces dissolved by acid from below rather than carved by rivers or enlarged by percolating rainwater. The caverns remain stable, their ceilings arched in shapes that distribute weight efficiently, demonstrating how even voids in rock can persist for millions of years when geometry favors stability. The Teton Range in Wyoming rises abruptly from the valley floor with no foothills to soften the transition, creating one of the most dramatic mountain fronts in North America. The Tetons are young, just 6 to 9 million years old, which makes them infants in geological terms. They're rising still along the Teton Fault, where the western block is being thrust upward, while the eastern block, Jackson Hole, drops down. The fault remains active. Earthquakes continue along it, indicating ongoing movement. The total displacement is around 30,000 feet when you combine the uplift of the mountains and the subsidence of the valley. Most of this displacement is hidden. Sediment fills Jackson Hole to depths of thousands of feet, masking how far the valley has actually dropped. The mountains themselves are carved from Precambrian metamorphic and igneous rocks, stone that formed 2.5 billion years ago, but was buried deep in the crust until recent fault movement brought it to the surface and raised it to alpine heights. Glaciers have since carved the peaks, creating the sharp spires and U-shaped valleys that make the Tetons visually striking. But the essential character of the range, its abrupt rise, its lack of foothills, its youth and vigor, comes from active faulting, from the ongoing process that continues lifting stone toward the sky. Michigan's Keweenaw Peninsula contains the world's largest concentration of native copper, pure metallic copper found as nuggets and sheets and veins in the rock, rather than as ore minerals that require smelting. 1.1 billion years ago, during the mid-continent rift, basaltic lava flows poured across the region. These flows contained small amounts of copper distributed throughout. Then, mineral-rich fluids circulated through the cooled basalt, dissolving the dispersed copper and redepositing it in concentrated form in vesicles, fractures, and between lava flows. The result was copper in nearly pure form, easily worked by prehistoric peoples who mined it thousands of years before European contact. Some copper masses weighed many tons, requiring extensive effort to extract and process. The copper occurs in the spaces between lava flows, in the tops of flows where gases created bubble-like vesicles, along faults and fractures. Mining began in prehistoric times and continued through the 19th and 20th centuries, extracting billions of pounds of copper. The deposits are now largely exhausted, but the peninsula preserves the evidence of this unusual geological concentration, where volcanic activity and hydrothermal circulation combined to create conditions that concentrated a dispersed metal into miniable masses of native copper. The Snake River Plain stretches across southern Idaho in a distinctive arc, each segment progressively older, moving from Yellowstone westward. This pattern reveals the track of the Yellowstone hotspot, a deep mantle plume that remains relatively stationary, while the North American plate drifts southwest over it. 16 million years ago, the hotspot was beneath what is now northern Nevada. As the continent moved, the hotspot burned through at different locations, creating a chain of volcanic calderas. Each caldera erupted catastrophically, collapsed, then was gradually filled with subsequent lava flows and sediment. The Snake River flows through this volcanic plain, cutting canyons in places through layer upon layer of basalt. The plain itself is relatively flat, a landscape built from countless lava flows that spread out from various vents, filling topography and creating a broad, gently sloping surface. The progression of volcanic activity from west to east tells the story of plate motion, each ancient caldera marking where the hotspot broke through, each location now dormant as the plate carried it away from the heat source below. Yellowstone represents the current position, the present moment in a process that has been creating the Snake River Plain for millions of years, and will continue creating new volcanic features as North America continues its patient drift. Natural Bridge in Virginia stands 215 feet tall and 90 feet wide, a limestone arch carved by Cedar Creek over thousands of years. Once owned by Thomas Jefferson, who purchased it from King George III and saw in it both natural wonder and potential tourism. The bridge represents a common, but always impressive geological process, the creation of natural arches through erosion. Cedar Creek once flowed across limestone bedrock, gradually dissolving a path through the rock. Where the limestone contained weaknesses, fractures, zones of different composition, the water worked faster, creating an underground passage. Eventually, the passage enlarged enough that the creek flowed entirely through it, abandoning its surface channel. The rock above remained stable, forming a natural bridge across the creek. The process continues. The creek still flows beneath the arch, still slowly expands the passage. Eventually, given enough time, the bridge will collapse, will become simply a wide opening between cliffs, will finally erode into a valley with no bridge at all. But for now it stands, stable enough to have carried a road across it for many years, solid enough to seem permanent, a reminder that rock can be both strong and ephemeral, that even stone yields to patient water. The Pierre Shale underlies much of South Dakota and represents the ancient seabed of the Western Interior Seaway, a vast, shallow sea that split North America in half 80 million years ago. The seaway stretched from the Arctic Ocean to the Gulf of Mexico, turning the continent into two separate landmasses with an inland ocean between them. In these warm, shallow waters, microscopic organisms drifted and died, their remains settling onto the seafloor in a slow rain of organic matter mixed with clay particles. Layer upon layer accumulated, each thin band representing years or decades of deposition, until the shale reached thicknesses of hundreds of feet. The western interior seaway eventually drained as the land uplifted, as the Rocky Mountains began their rise and changed drainage patterns across the continent. What remains is the Pierre Shale, a soft gray rock that weathers easily, creating rolling topography and badlands where exposed. Fossils of marine reptiles, mosasaurs and plesiosaurs, are occasionally found in the shale, reminders that this landlocked region was once ocean. The rock itself is monotonous in appearance, but profound in implication, evidence that sea level and continental configuration are not permanent, that what is now grassland was once sea floor, that geography remains fluid across geological time. California's White Mountains host bristlecone pines growing on dolomite soil so alkaline and nutrient-poor that almost no other plants can survive. These harsh conditions paradoxically allow the bristlecone pines to thrive, free from competition and from many diseases and pests that require richer environments. The oldest living tree is over 4,800 years old, making it the oldest known individual organism on Earth. It was already ancient when the pyramids were new, was growing when mammoths still walked the planet, has survived drought and storm for nearly 5 millennia. The trees grow incredibly slowly in this harsh environment, sometimes adding barely a millimeter of thickness in a good year. This slow growth creates dense wood that resists decay, allowing dead trees to remain standing for thousands of additional years, their twisted forms sculpted by wind and ice. The trees serve as geological timekeepers. Their growth rings preserve a record of climate variations spanning thousands of years, each ring reflecting the conditions of a single growing season. Scientists use these trees to calibrate radiocarbon dating, to reconstruct ancient climate patterns, to understand how Earth systems have varied across millennia. The bristlecone pines endure not despite the harsh geology, but because of it, their longevity a function of the unforgiving dolomite soil that eliminates competition. The Balcones Fault Zone near Austin, Texas, marks a distinct boundary between the Gulf coastal plain and the hill country, a geological transition so sharp it creates visible changes within feet. Cross the fault zone, and the topography shifts from flat coastal plain to rolling hills. The bedrock changes from younger, soft limestone to older, harder limestone and granite. Even the vegetation transforms, oak and juniper replacing coastal prairie plants. The fault zone formed 30 million years ago as the Gulf Coast subsided, while the interior remained relatively stable, creating a series of parallel faults along which the coastal block dropped down. The displacement totals hundreds of feet in places, though much of it is hidden beneath younger sediments. Springs emerge along the fault zone, where water flowing through porous limestone encounters impermeable rock and is forced to the surface. These springs, including Barton Springs in Austin, provided crucial water sources for both prehistoric and modern settlements. The Balcones Fault Zone is still seismically active, generating small earthquakes occasionally, reminding residents that the boundary remains dynamic. Stand on the fault, and you stand on a geological dividing line, a place where the character of the Earth changes fundamentally within a few steps. Mauna Kea on Hawaii's Big Island rises 13,800 feet above sea level, but measured from its true base on the ocean floor, it stands 33,500 feet tall, taller than Mount Everest when both are measured from base to summit. The mountain is not a single structure, but rather the accumulated result of hundreds of thousands of volcanic eruptions over 700,000 years. The Hawaiian Islands sit above a hot spot in the Earth's mantle, a plume of unusually hot rock rising from deep below. As the Pacific Plate moves northwest over this stationary hotspot, the plume burns through, creating volcanoes. Each Hawaiian island represents a different stage in this process. The Big Island sits currently over the hotspot and remains volcanically active, while islands to the northwest are progressively older and more eroded. Mauna Kea itself last erupted 4,500 years ago and is considered dormant, though not extinct. Its summit hosts astronomical observatories, taking advantage of the altitude, stable atmosphere, and distance from city lights. The mountain's name means White Mountain in Hawaiian, referring to the winter snow that caps its summit despite the tropical latitude. An unusual sight in the Pacific, stone rising so high that it reaches into cold upper atmosphere, collecting snow that seems incongruous in these latitudes. The Ogallala Aquifer beneath the Great Plains represents water accumulated over thousands of years, stored in sand and gravel, deposited by ancient rivers flowing east from the Rocky Mountains. The aquifer extends from South Dakota to Texas, underlying 8 states and supplying 30% of America's irrigation water. But the water it holds is largely fossil water, precipitation that fell during wetter climate periods following the last ice age, water that accumulated when recharge exceeded extraction. Today, the aquifer is being depleted approximately 10 times faster than natural processes can replenish it. Water levels have dropped by more than 100 feet in some areas, forcing wells to be drilled deeper, increasing pumping costs, sometimes exhausting the aquifer entirely. The high plains above the aquifer were once grassland, then were converted to agriculture possible only because of groundwater irrigation. As the aquifer depletes, some regions are returning to dryland farming or grassland, completing a cycle from prairie to farmland and back. The Ogallala represents the collision between geological time and human time. Water that took 10,000 years to accumulate being extracted in decades, a resource that appeared limitless, revealing itself as finite, forcing questions about sustainability and the relationship between agriculture and geology. Seneca Rocks in West Virginia rises 900 feet as a narrow fin of Tuscarora quartzite, tilted nearly vertical by the forces that built the Appalachian Mountains. The quartzite began as beach sand deposited along the margin of an ancient continent 440 million years ago. Then came the collision that created the Appalachians. The sand was buried, compressed, heated until the grains fused into hard quartzite, then tilted nearly 90 degrees as the crust folded and fractured. After the mountains formed, erosion began its patient work, removing softer surrounding rocks and leaving the resistant quartzite standing as a dramatic fin aligned north-south. The rock is strong enough for technical climbing, fractured enough to provide cracks and ledges for holds. From certain angles, Seneca Rocks appears impossibly thin, a blade of stone that seems too narrow to remain standing. But the tilted bedding creates internal strength. The near vertical orientation sheds water efficiently, and the quartzite resists weathering. The formation has become an icon of Appalachian geology. Stone that demonstrates how ancient beaches can become mountain ridges, how tectonic forces can rotate rock layers from horizontal to vertical, how differential erosion reveals the history written in stone by removing the weak and preserving the strong. The Black Hills of South Dakota rise abruptly from the surrounding plains, a geological oddity consisting of an isolated mountain range far from any plate boundary or obvious tectonic cause. 60 million years ago, a massive granite batholith pushed upward from depth, doming and fracturing the overlying sedimentary rock layers. The uplift created a bullseye pattern visible from space, concentric rings of different rock types exposed in cross-section as erosion removed the dome's top. At the center lies Precambrian granite and metamorphic rock, some of the oldest stone in North America. Surrounding this core, progressively younger sedimentary layers, limestone, sandstone, shale, tilt outward from the central uplift. The outer edge consists of a prominent ridge of resistant limestone and sandstone, the hogback that encircles the entire range. Rivers flowing outward from the central uplift cut through these concentric rock layers, creating scenic canyons and valleys. The Black Hills continue rising slowly, pushed by processes not entirely understood. Perhaps residual effects of the original uplift, perhaps deeper mantle dynamics. The range hosts Mount Rushmore, carved into granite that formed 1.7 billion years ago. Presidential faces sculpted in stone that predates complex life on Earth. An interesting juxtaposition of human history measured in centuries against geological history measured in eons. The Palos Verdes Peninsula in Southern California rises gradually from the ocean, thrust upward along faults at a rate of approximately half a foot per 1,000 years. This seems impossibly slow until you consider the accumulated result. Ancient wave-cut terraces now stand hundreds of feet above the sea, each terrace representing a former beach when the peninsula was lower. You can walk these terraces, reading the landscape like a staircase that records uplift. The lowest, youngest terrace sits just above current sea level. Higher terraces date back tens of thousands of years, their elevation a function of uplift rate and the time elapsed since they formed. Between major terraces, minor ones mark smaller pauses in sea level or pulses of uplift. The terraces aren't perfectly preserved. Erosion softens their edges. Development has modified some, but the pattern remains clear. Fossils in the terrace sediments match modern local species, indicating the marine environment hasn't changed fundamentally, even as the land rose. The peninsula demonstrates how landscapes that appear stable are actually dynamic, how land thought of as fixed relative to sea is actually moving, rising imperceptibly but measurably, building elevation through the accumulated effect of small movements repeated over long spans of time. Flaming Gorge in Utah cuts through sedimentary rock layers spanning 2.5 billion years, each colored band visible in the canyon walls, representing vastly different environments and eras. At the bottom lie the oldest rocks, Precambrian metamorphic stone formed in mountain-building episodes so ancient they predate most life on Earth. Above these sit younger layers, red sandstones from ancient deserts, gray limestones from shallow seas, cream-colored shales from river deltas, each formation telling its own story. The canyon walls display this stratified history in brilliant colors: reds and oranges from iron oxide, grays from organic matter, creams and tans from pure limestone, creating the flaming appearance that gives the gorge its name. The Green River carved this canyon, cutting down through the layers over millions of years as the region slowly uplifted. Unlike the Grand Canyon, which exposes primarily Paleozoic rocks, Flaming Gorge reveals a deeper span including some of Earth's oldest stone. Walk the rim or descend toward the water, and you walk through geological time, passing from relatively recent sediments down through progressively older layers, approaching rocks that formed when Earth was young, before oxygen accumulated in the atmosphere, before continents assembled into their current forms. The Old Man of the Mountain in New Hampshire stood as a natural granite profile visible from below until it collapsed in 2003, ending an existence that had lasted perhaps 12,000 years. The formation appeared after the last glaciation, when ice retreated from the White Mountains. Glacial activity had left granite exposed on the cliff face, with natural fractures and zones of weakness, creating blocks of stone that from a specific viewpoint resembled a human profile. Freeze-thaw cycles continued working on these blocks, water seeping into cracks, freezing, expanding, gradually loosening the stone. The profile that looked stable was actually slowly failing, held temporarily by the balance of remaining stone and gravity. Cables and turnbuckles installed in the 20th century attempted to preserve the formation, to hold together what geology intended to dismantle. But on a spring night in 2003, after a particularly harsh winter, the face collapsed, the individual sections tumbling down the cliff. What remains are photographs and memories, and the cliff face itself now changed, no longer presenting that familiar profile. The old man demonstrates geology's indifference to human meaning. We saw a face and valued it, placed it on state quarters and license plates, but to erosion it was simply fractured granite, subject to the same weathering processes affecting all exposed rock. The formation's collapse was not tragic from a geological perspective, but rather inevitable, another moment in the slow reduction of mountains. The Valle Caldera in New Mexico spreads 12 miles wide, a volcanic depression created 1.25 million years ago by an eruption that ejected 150 cubic miles of rock and ash across the southwest. To comprehend this scale, the 1980 Mount St. Helens eruption displaced roughly 1/4 cubic mile. Valles ejected 600 times that amount. The eruption evacuated so much magma from the chamber beneath the volcano that the mountain's summit had nothing supporting it and collapsed inward, creating the caldera. Ash from the eruption, called the Bandelier Tuff, spread across the region, eventually cooling and welding into solid rock that has been carved by erosion into dramatic canyons and mesas. Inside the caldera, a resurgent dome has since pushed upward as new magma accumulated below, creating mountains within the caldera itself. Hot springs and fumaroles persist, evidence that the volcanic system remains active, though dormant. Geothermal wells have been drilled to study the heat and potentially harness it. The caldera floor hosts grasslands and forests, beautiful terrain that obscures the violent origin. Few landscapes so dramatically demonstrate the scale of volcanic processes, the capacity of Earth to excavate itself, to hollow out mountains and spread their contents across hundreds of miles, to create voids that then partially refill as the system readjusts and new magma rises beneath the caldera floor. Grandfather Mountain in North Carolina features quartzite cliffs over 1 billion years old, some of the oldest exposed rocks in the eastern United States. The quartzite formed from beach sand deposited along an ancient continental margin, sand that was later buried, compressed, heated, until the individual grains fused into solid rock. This was long before complex life evolved on Earth, before plants colonized land, before animals ventured from the oceans. The continent these beaches bordered has long since fragmented and reassembled into different configurations. What remained was the quartzite, resistant to erosion, later uplifted during the formation of the Appalachians, and now standing as high peaks and dramatic cliffs. The mountain's name comes from the appearance of its profile, which from certain angles suggests a reclining figure. The rocks themselves preserve ripple marks from ancient waves, cross-bedding from tidal currents, occasionally preserved raindrop impressions, small details that survived metamorphism and provide windows into conditions on a billion-year-old beach. Stand on Grandfather Mountain and you stand on stone that predates almost all the fossils paleontologists study, that formed in an Earth radically different from today's, that has endured through the full span of complex life's evolution and diversification, through ice ages and warming periods, through the rise and erosion of mountain ranges, patient and persistent, across time spans that reduce all human history to an instant. The Wasatch Fault stretches 240 miles along Utah's Wasatch Range, a boundary between mountain and valley that remains dangerously active. The fault is capable of producing earthquakes of magnitude 7.5 or greater, events that would be catastrophic for the urban corridor along the range's western base, where most of Utah's population lives. Geological evidence shows the fault ruptures in major earthquakes roughly every 1,300 years, with different segments breaking at different times. Some sections haven't ruptured in over 1,000 years and are considered overdue. The fault is clearly visible in the landscape. The Wasatch Front, where mountains rise abruptly from valleys, marks exactly where the Western Bloc has been dropping while the Eastern Bloc rises. The total displacement over millions of years exceeds 20,000 feet when combining mountain uplift and valley subsidence. Ancient shorelines from Lake Bonneville, a vast Ice Age lake that once covered much of western Utah, are offset vertically by the fault, showing how earthquakes have repeatedly ruptured the surface. The fault represents ongoing mountain building, the Wasatch continuing to rise as the Basin and Range province stretches east-west. Mountains we might assume are stable, products of ancient collisions now merely eroding, are actually growing still, being actively uplifted by faults that accumulate stress and release it episodically in the earthquakes that reshape the landscape and occasionally reshape human communities as well. Crater of Diamonds. State Park in Arkansas sits atop an ancient volcanic pipe where diamonds formed 100 miles beneath Earth's surface 95 million years ago and were explosively brought upward in a single violent eruption. Diamonds require extraordinary pressure to form, pressures only available deep in the mantle where carbon atoms are forced into the dense crystalline structure that makes diamond the hardest natural material. Normally, diamonds carried toward the surface would revert to graphite as pressure decreased and temperature remained high. But volcanic pipes bring material upward so rapidly, at speeds exceeding 100 miles per hour through vertical conduits, that there's no time for the diamonds to transform. They reach the surface still locked in their high-pressure form, embedded in a rock called kimberlite that forms specifically in these violent eruptions. The Arkansas pipe is now eroded, exposing the kimberlite at the surface where visitors can search for diamonds. The park is the only diamond mine in the world open to the public with a finders keepers policy. Stones found here range from tiny chips to gems weighing multiple carats. Each diamond represents a piece of the deep mantle brought to the surface in a geological instant, a fragment of the planet's interior that normally remains forever inaccessible, carried upward by the same violent process that created the crater, now worn nearly flat by erosion. The Beartooth Highway in Montana crosses a high plateau composed of rock 3 billion years old, among the oldest on Earth's surface. The rock formed when the planet was barely 1/3 its current age, when day was shorter, when the moon appeared larger in the sky, when the atmosphere contained almost no oxygen. These ancient metamorphic rocks, gneiss and schist and granite, formed deep in the crust of an ancient mountain range, were eventually exposed by erosion, then sat at or near the surface for over 2 billion years. 75 million years ago, the region was uplifted during the Laramide orogeny that built the Rocky Mountains, raising this ancient basement rock to elevations exceeding 10,000 feet. Glaciers then carved the plateau during the ice ages, creating U-shaped valleys, cirques, and alpine lakes. The highway crosses this landscape at elevations reaching nearly 11,000 feet, making it one of the highest roads in North America. The views are expansive, mountains stretching to distant horizons, valleys carved thousands of feet deep, lakes reflecting sky and stone. But the real wonder lies beneath the pavement, in rock that predates nearly all visible life on Earth, that formed when continents were still assembling into their first stable configurations, that has survived 3 billion years of planetary history, and now supports a highway where travelers cross this ancient terrain in minutes, traversing in an afternoon what took eons to create. Florida's sinkholes form suddenly when the limestone bedrock beneath the surface dissolves and collapses, creating depressions that can swallow houses, cars, roads, anything unfortunate enough to be present when the ground gives way. The limestone underlying Florida is soluble in slightly acidic water, and rainwater becomes acidic as it absorbs carbon dioxide from the atmosphere and soil. Over time, this acidic water percolates underground, dissolving pathways and caverns in the limestone. As long as the water table remains high, water filling the caverns provides support. But when the water table drops due to drought or groundwater pumping, support is lost and voids collapse. Sometimes the collapse is gradual, creating a gentle depression. Sometimes it's catastrophic, opening a hole in seconds. Florida's karst topography makes sinkholes inevitable and unpredictable. New sinkholes appear regularly across the state, some large enough to swallow buildings, others small enough to repair easily. The phenomenon reveals the temporary nature of apparent solidity. Ground that seems stable is actually gradually dissolving below, maintained temporarily by water pressure or by a thin layer of soil bridging an underground void. Eventually, the bridge fails, the void reaches the surface, and what was solid ground becomes open air. Sinkholes represent geology happening at human timescales, the dissolution and collapse visible within lifetimes rather than eons. The Columbia River Gorge between Washington and Oregon was carved not primarily by the river's normal flow, but by catastrophic floods from glacial Lake Missoula. The gorge is wider and deeper than the Columbia River alone could have created, its walls showing evidence of high-velocity water scouring bedrock far above the current river level. The floods moved with such power they transported house-sized boulders, stripped soil from hillsides, carved channels through solid basalt. Where the water encountered narrow sections, it pooled temporarily, creating temporary lakes that then drained catastrophically when barriers failed or water levels rose high enough to overtop them. The floods occurred repeatedly. Lake Missoula formed and failed dozens of times as ice dams grew and collapsed. So the gorge records not one disaster but many, each flood enlarging and reshaping what previous floods had carved. Today, the gorge is scenic and relatively calm, the Columbia flowing peacefully through a canyon that seems oversized for the current river. Waterfalls cascade down the gorge walls where tributary streams encounter the deeply carved main valley. The climate transitions dramatically along the gorge, from wet forests on the western end to dry grasslands in the east, all contained within a canyon shaped by water moving at volumes and speeds that no longer occur. The gorge is a monument to catastrophe, rendered peaceful by time. Chimney Rock in western Nebraska rises 300 feet as a slender spire visible for miles across the plains, a landmark that guided travelers on the Oregon Trail and Mormon Trail westward. The rock consists of volcanic ash and clay from eruptions in what is now Yellowstone, ash that settled across the Great Plains 30 million years ago and gradually compacted into soft rock. Erosion has been wearing the formation down ever since, removing surrounding material and isolating chimney rock as a remnant. The spire is fragile. Chunks of rock fall from it regularly, particularly during freeze-thaw cycles when water expands in cracks and breaks off pieces. Early travelers' descriptions mention the rock being taller than it is now, and measurements confirm it has lost significant height over the past 2 centuries. Eventually, likely within centuries rather than millennia, the narrow spire will erode away entirely, leaving only the broader base. But for now it stands, improbable and distinctive, a finger of soft rock pointing skyward in an otherwise flat landscape. The rock serves as a reminder that even seemingly permanent landmarks are temporary on geological timescales, that what appears solid is actually crumbling, that the landscapes we mark on maps and carry in memory are themselves in flux, changing slowly but inevitably as wind and water and frost do their patient work of reduction. White Sands National Park in New Mexico contains dunes composed entirely of gypsum crystals, creating a landscape of pure white that extends across 275 square miles. The gypsum eroded from surrounding mountains, primarily the San Andres and Sacramento ranges, where it formed as evaporate deposits in ancient seas. Rain and snowmelt dissolve the gypsum and carry it down into the Tularosa Basin, a closed depression with no outlet to the ocean. There, the water evaporates, leaving gypsum crystals behind. Wind picks up the crystals and builds them into dunes that shift and reshape constantly. The dunes squeak when walked upon, a distinctive sound created by the friction of crystals sliding past each other. Unlike sand dunes, which can burn feet on hot days, gypsum dunes remain relatively cool because the white surface reflects most solar radiation. The dunes are inhospitable to most plants and animals, but a few species have adapted. Lizards and mice have evolved white coloration matching the gypsum, and specialized plants tolerate the gypsum-rich soil. The landscape appears otherworldly, more like snow than sand, creating optical effects and photography opportunities unlike anywhere else. The dunes represent an unusual convergence of geology and geography. Evaporate minerals, closed drainage basin, persistent wind, that creates a rare and striking landscape where chemistry and physics combine to turn dissolved gypsum into mobile, gleaming hills of white crystal. Craters of the Moon. National Monument in Idaho preserves basaltic lava flows so young, between 2,000 and 15,000 years old, and so well preserved that NASA used the site to train Apollo astronauts for lunar missions. The basalt erupted from fissures along the Great Rift, a 62-mile-long zone of volcanic vents cutting through the Snake River Plain. The eruptions produced several types of volcanic features: cinder cones built from airborne ash and cinders, spatter cones formed from lava fountains, lava tubes created when the surface of a flow cooled while interior lava drained away. The surface displays remarkable textures: Pahoho with its smooth, ropey appearance, and AA with its rough, clinkery surface. Vegetation is sparse, limited to plants that can tolerate the porous, low-nutrient basalt and the harsh conditions at 4,800 feet elevation. The landscape appears stark and barren, particularly in summer when temperatures soar and the black rock becomes too hot to touch. But the flows preserve fine details of their formation: frozen lava waterfalls, skylights where lava tube roofs collapsed, tree molds where lava flowed around living trees and preserved their shapes in stone. The monument offers a view of volcanism rarely available. Eruptions recent enough that weathering hasn't softened the features, flows preserved in the dry climate with extraordinary detail. a landscape that demonstrates how basaltic volcanism creates terrain one flow at a time, building plains through repeated eruptions. The Needles in South Dakota's Custer State Park rise as granite spires eroded into dramatic pinnacles, their distinctive shapes created by the intersection of geology and time. The granite itself, formed 1.7 billion years ago as a massive batholith, molten rock that cooled slowly underground, developing a coarse crystalline structure. As it cooled, the granite developed vertical fractures, planes of weakness running through the rock. Then came uplift and exposure, the removal of overlying rock until the granite itself stood at the surface. Water seeped into the fractures, freezing and expanding, widening the cracks. Chemical weathering attacked the granite along these weakened zones. Gradually, the solid rock separated into columns aligned along the fracture patterns. Further, weathering rounded the columns, carved them into the needle-like spires visible today. The needles demonstrate how fracture patterns control erosion. Rock that appears homogeneous actually contains internal structure, invisible planes of weakness that determine how the stone will ultimately break down. Drive through the Needles Highway, and you pass between these granite spires, some narrow enough that the road barely fits, others forming broader towers. Each spire represents resistant granite separated from its neighbors by fractures that erosion exploited and widened. The formation continues evolving. Frost wedging persists, chemical weathering continues, each winter adding tiny increments to the slow process of separation and reduction. The Great Salt Lake in Utah fluctuates dramatically in size depending on precipitation and evaporation, sometimes covering over 2,000 square miles, other times shrinking to less than 1,000. The lake is a remnant of ancient Lake Bonneville, which once covered 20,000 square miles of the Great Basin and reached depths of 1,000 feet. 14,500 years ago, Lake Bonneville catastrophically breached its northern rim at Red Rock Pass, releasing water equivalent to the flow of the Amazon River sustained for 8 weeks. The flood scoured the Snake River Plain, moved house-sized boulders hundreds of miles, carved channels through bedrock. After this dramatic drainage, the lake gradually evaporated over thousands of years, leaving behind the Great Salt Lake, Utah Lake, and various smaller water bodies, along with ancient shorelines visible as terraces on mountain slopes throughout the basin. The Great Salt Lake has no outlet, so water leaves only through evaporation, concentrating dissolved minerals until the lake becomes several times saltier than the ocean. Brine shrimp thrive in these conditions, creating a pink hue in some areas and supporting migratory bird populations. The lake is actually divided into northern and southern sections by a railroad causeway, with different salinity levels in each. As climate changes and water diversions continue, the lake shrinks, exposing lakebed that releases dust storms, affecting air quality. The Great Salt Lake represents the final chapter of Lake Bonneville's story, a remnant gradually evaporating, perhaps eventually disappearing entirely unless climate patterns shift to favor accumulation over loss. The Finger Lakes of New York stretch north-south across the landscape like parallel scratches, each lake occupying a glacially carved valley that filled with water when ice retreated. During the Ice Ages, glaciers advanced southward from Canada, their massive weight grinding down existing river valleys, deepening and widening them into U-shaped troughs. The ice moved slowly but with irresistible force, quarrying rock from valley walls, carrying sediment, reshaping topography. When the climate warmed and ice retreated, the over-deepened valleys filled with meltwater, creating the 11 main Finger Lakes. Some lakes are remarkably deep. Seneca Lake reaches over 600 feet, with portions of its floor lying below sea level despite the lake sitting at relatively high elevation. The parallel orientation of all the lakes reveals the direction of ice flow, aligned perfectly north-south. The valleys show classic glacial features. Hanging valleys where tributaries enter the main valley high above the current water level, creating waterfalls. Moraines at the southern ends where glaciers deposited rock debris. Steep sides where ice plucked stone from valley walls. The Finger Lakes region demonstrates glacial erosion at its most systematic, not random scouring, but rather focused deepening of existing valleys, creating a landscape of extraordinary regularity, where lake after lake follows the same orientation, each one a water-filled valley carved by ice that arrived from the north and departed the same direction. The Maroon Bells near Aspen, Colorado display distinctive reddish rocks that photograph beautifully against autumn foliage and snow-capped peaks. The color comes from iron oxide, essentially rust, staining sedimentary rocks deposited 300 million years ago. At that time, the area was not mountainous, but rather a low-lying coastal or near-coastal environment, receiving sediment from highlands to the west. Rivers carried mud and sand that accumulated in layers, building up sequences hundreds of feet thick. The iron in the sediments oxidized in the presence of oxygen, creating the red coloration preserved when the sediments turned to stone. Much later, just 70 million years ago, tectonic forces uplifted the region, tilting and folding these sedimentary layers, pushing them to elevations exceeding 14,000 feet. The Maroon Bells themselves are peaks of particularly resistant rock that weathered more slowly than surrounding material. But the distinctive red and purple colors remain the most notable feature, making these mountains visually distinctive even in a state filled with spectacular peaks. The rocks are relatively weak compared to granite or quartzite. The mudstone and sandstone weather readily, creating unstable slopes prone to rockfall and avalanche. The beauty comes at a cost in terms of instability. But the color, that deep maroon stained by iron oxide 300 million years ago, persists through uplift and erosion, giving these mountains their name and their character. The Outer Banks of North Carolina form a chain of barrier islands constantly reshaped by waves, wind, and storms, demonstrating that not all geology operates on timescales of millions of years. Barrier islands are inherently temporary features, sand deposits that migrate, breach, reform, always in motion. Waves approaching the shore at an angle move sand along the beach in a process called longshore drift. Storms wash sand from the ocean side to the sound side, causing islands to migrate landward over time. Inlets open and close as storms breach the islands, or as sand deposition seals previous openings. The islands provide no solid foundation. They're entirely unconsolidated sand, mobile sediment shifted by every significant storm. This mobility threatens human structures, requiring constant maintenance and occasional relocation. Cape Hatteras Lighthouse, built in 1870, originally stood 1,500 feet from the ocean. By 1999, erosion had brought the ocean to within 120 feet, forcing the National Park Service to physically move the lighthouse 2,900 feet inland. The move took 23 days, with the lighthouse traveling along steel beams at a rate of inches per hour. The Outer Banks teach a fundamental lesson about building on barrier islands. The substrate itself is temporary, sand that belongs to the ocean and is merely borrowing time as land. The islands will persist in some form, but their exact configuration changes continuously, shorelines retreating and advancing, inlets opening and closing, the whole system in constant flux. Fossil Butte in Wyoming preserves 50-million-year-old fish fossils in such exquisite detail that scales, fins, and even stomach contents remain visible, frozen in limestone that formed on the bottom of an ancient lake. During the Eocene epoch, southwestern Wyoming hosted a vast lake system covering thousands of square miles. The climate was subtropical, supporting palms and crocodiles at latitudes that are now temperate. Fish populations thrived in the warm waters. When fish died and sank to the lake bottom, fine-grained sediments buried them quickly, before scavengers could disturb the remains or decay could destroy the tissue. The anoxic conditions on the lake floor further aided preservation. No oxygen meant no aerobic bacteria to decompose the carcasses. Over millions of years, more sediment accumulated, compressing the lower layers into limestone. The result is a fossil assemblage of remarkable quality, where individual scales can be counted, where the curve of the spine is preserved perfectly, where sometimes the last meal remains visible in the body cavity. Commercial fossil quarries operate in the area, extracting slabs of limestone that, when split carefully along bedding planes, reveal perfect fish fossils. Museums and private collectors worldwide display Fossil Butte specimens. The site represents one of those rare geological moments when preservation conditions were ideal, when rapid burial and anoxic environments combined to create a snapshot of ancient life preserved in stone with a clarity that makes 50 million years seem like yesterday. The Mississippi River Delta extends into the Gulf of Mexico, building land from sediment carried from 31 states and 2 Canadian provinces, from a drainage basin covering 40% of the continental United States. Every flood, every spring, runoff carries soil eroded from the interior, transporting it downstream in suspension. When the river reaches the Gulf, its velocity drops, its capacity to carry sediment decreases, and the suspended material settles out, building the delta forward at roughly 200 feet per year, a rate that has slowed significantly due to upstream dams trapping sediment and levees preventing the river from flooding across its natural floodplain. The delta is not a single feature, but rather multiple lobes representing different eras when the river flowed through different channels. Every few thousand years, the Mississippi would abandon its current course for a shorter, steeper path to the Gulf, building a new delta lobe while the old one subsided and eroded. 7 distinct lobes have been identified, each representing a different chapter in the delta's construction. Currently, the river is maintained artificially in its present course past New Orleans, prevented from shifting naturally to the Atchafalaya. Meanwhile, the existing delta is subsiding and eroding, losing land because sediment input has decreased and sea level is rising. The Louisiana coast loses roughly 1 football field of land every 100 minutes, a dramatic rate of loss that demonstrates how deltas require constant sediment input to maintain themselves against the ocean's patient work of removal. The Valley of 10,000 Smokes in Alaska was created in 1912 when the Novarupta volcano erupted with 30 times the force of Mount St. Helens, ejecting more than 3 cubic miles of magma in 60 hours. The eruption was so catastrophic that nearby Mount Katmai's summit collapsed when magma beneath it migrated laterally to feed the Novarupta eruption, creating a caldera 3 miles wide. The ejected material, ash, pumice, and hot gas, poured down a river valley, filling it to depths of 700 feet, with deposits so hot they took decades to cool. Steam and volcanic gases vented from countless fumaroles across the valley floor, creating the smokes that gave the valley its name. When explorers first visited in 1916, They reported thousands of vents releasing steam and gas, some with enough force to be heard from miles away. Over subsequent decades, the valley cooled and most fumaroles ceased, but erosion has carved deep canyons through the ash deposits, revealing the internal layering of the flow. The valley demonstrates the power of volcanic eruptions to reshape landscape instantaneously in geological terms. What was a mountain valley became a flat plain of volcanic deposits 700 feet deep in less than 3 days. The eruption was one of the largest of the 20th century, yet occurred in such a remote location that it caused minimal human casualties. Now the valley stands as a monument to volcanic violence, gradually eroding, gradually revealing the structure of the deposits, a landscape frozen in the moment of catastrophe and slowly returning to something resembling its pre-eruption form. The Sangre de Cristo Mountains in southern Colorado and northern New Mexico contain some of the southernmost glacially carved cirques in North America. Bowl-shaped depressions carved into mountainsides by glaciers that occupied these high valleys during the Pleistocene ice ages. Between 12,000 and 30,000 years ago, when global climate was cooler, snow accumulated in these high valleys faster than it melted. The snow compressed into ice, formed small glaciers that carved into the mountain through freeze-thaw weathering and plucking. The process where water seeps into cracks in rock, freezes, expands, and breaks off chunks that the glacier then carries away. Over thousands of years, these mountain glaciers carved deep into the peaks, creating the distinctive cirque shape. Steep headwalls, relatively flat floors, often containing small lakes called tarns. When climate warmed and glaciers retreated, the cirques remained as evidence of past ice. The Sangre de Cristo cirques are particularly notable because they formed at relatively southern latitudes. Their existence required high elevation to provide cold enough conditions for glaciers to persist. The mountains themselves rise to over 14,000 feet in places, high enough that even at southern latitudes, ice could accumulate and flow. The cirques represent the intersection of latitude, elevation, and climate, places where conditions aligned to allow alpine glaciation at the southern edge of its range in the Rockies. Indiana limestone, quarried near Bloomington, has built more than 35% of America's notable buildings, including the Empire State Building, the Pentagon, the National Cathedral, and countless other structures of architectural significance. The limestone formed 330 million years ago from the compressed remains of marine organisms, primarily crinoids, which are relatives of starfish, that lived in shallow seas covering the region during the Mississippian period. As these organisms died, their calcium carbonate skeletons accumulated on the seafloor, building up in beds that eventually reached hundreds of feet thick. Compression over time turned the loose sediment into solid limestone. What makes Indiana limestone valuable is its uniform texture and consistency. The stone can be cut precisely in any direction without splitting or breaking along unpredictable planes. It carves cleanly, accepts fine detail, and weathers well in most climates. The stone is soft enough when freshly quarried that it can be shaped with handsaws, but hardens upon exposure to air, becoming more durable. The color is typically buff or gray, neutral tones that work well architecturally. Quarrying continues today in southern Indiana, where underground and surface mines extract blocks of limestone that are shipped nationwide. To look at America's monumental architecture is often to look at ancient Indiana seafloor, at compressed crinoid stems and shell fragments, now forming columns and facades, at stone that was life 300 million years ago and has been transformed into human monuments to permanence and significance. The Meramec Caverns in Missouri extend through 5 levels of passages carved from limestone by underground streams over millions of years. The limestone itself dates to the Mississippian period, formed from marine sediments when a warm, shallow sea covered the region. After the limestone solidified, slightly acidic groundwater began percolating through it, following fractures and bedding planes, gradually dissolving pathways. Where water flow concentrated, passages enlarged. Where water pooled, chambers formed. The multi-level structure reflects changes in the water table over geological time. As the Meramec River cut down through the landscape, the water table lowered, abandoning upper cave passages and creating new passages at lower elevations. The caverns are known for both their geological features, massive flowstone formations, delicate stalactites, stalagmites in fantastic shapes, and their colorful history as a hideout for Jesse James and his gang. The cave's large rooms provided shelter. Its multiple entrances offered escape routes. Its limestone walls held no record of those who passed through in darkness. The caverns continue developing today wherever water moves through them. Stalactites grow incrementally as mineral-rich water drips and leaves behind calcium carbonate. Flowstone builds, where water sheets across cave walls, each mineral deposit representing thousands of years of patient accumulation. The caves remind us that landscapes develop not just on the surface, but also beneath it. That as mountains erode upward, passages hollow out below. That stone's apparent solidity masks the slow work of dissolution. Grasshopper Glacier in Montana contains millions of locusts frozen in ice at 11,000 feet elevation, preserved from a storm centuries ago that caught the insects during migration and embedded them in the glacier. The locusts, actually Rocky Mountain grasshoppers, a species now extinct, would occasionally swarm in massive numbers during the 19th century, darkening skies and devastating crops across the Great Plains. The insects preserved in Grasshopper Glacier likely encountered a summer snowstorm while crossing the Beartooth Mountains, died from cold, and were buried in snow that compressed into glacial ice. As the glacier flows downslope, older ice containing locusts occasionally surfaces near the terminus, revealing the preserved insects. The glacier itself is retreating as climate warms, exposing more of its contents, but also threatening the long-term preservation of this unique biological archive. The frozen grasshoppers represent an accidental time capsule, insects that lived and died centuries ago, now visible in ice that has carried them slowly down mountain. The glacier demonstrates how ice preserves what other environments destroy. Soft-bodied insects that normally decay within days remain intact for centuries in frozen conditions. It also shows how glaciers concentrate and reveal what they preserve. The insects died scattered across snowfields, but are now concentrated in distinct dark bands within the ice. Bands that represent individual storms when conditions were right for mass mortality and subsequent burial. The Continental Divide in Rocky Mountain National Park separates watersheds draining to the Pacific Ocean from those flowing toward the Atlantic, a hydrological boundary marked by a subtle ridge where water falling on one side travels west and water falling inches away flows east. The divide seems momentous. It determines the ultimate destination of every raindrop and snowflake, yet it's often topographically understated, sometimes crossing broad saddles and gentle slopes rather than following dramatic peaks. In the Rockies, the divide generally follows the crest of the range, but its exact path wanders, sometimes departing from the highest summits to follow ridges that separate drainage basins. Stand on the divide, and you stand on a line where gravity makes its fundamental decision, where the physics of water flow determines whether a molecule begins a journey to the Pacific or the Atlantic, to the Gulf of Mexico or the Gulf of California. The concept extends beyond the Rockies. The continental divide runs from Alaska to South America, separating Pacific and Atlantic Gulf drainage across the entire hemisphere. But in Rocky Mountain National Park, the divide is accessible, hikeable, clearly marked, a place where the abstract concept becomes tangible landscape. The divide reminds us that topography controls drainage, that even subtle elevation differences determine flow direction, that the organization of rivers and watersheds reflects the underlying structure of mountains and valleys. Nevada's Basin and Range Province consists of over 400 parallel mountain ranges separated by flat valleys, a distinctive topography created as the Earth's crust stretches east-west and breaks into blocks. As extension occurs, as the crust is pulled apart by tectonic forces, it fractures along normal faults. Blocks between faults tilt, with one edge rising to form a mountain range and the other edge dropping to form a valley. This process has been active for roughly 30 million years and continues today, making the basin and range one of the most seismically active regions in North America. The characteristic pattern is visible from aircraft: range, valley, range, valley, range, repeating across hundreds of miles. The valleys fill with sediment eroded from the adjacent mountains, alluvial fans at range fronts, playa lakes in valley centers. Most valleys have internal drainage. Water flows in but not out, evaporating or seeping underground rather than reaching the ocean. The province demonstrates what happens when crust extends. It doesn't stretch uniformly, but rather breaks into blocks that move independently, creating dramatic topography from what was once relatively flat terrain. The basin and range has widened by roughly 300 miles over the past 30 million years, the crust thinning as it stretched, the moho, boundary between crust and mantle, rising as crustal thickness decreased. This ongoing extension will eventually open the region further, perhaps eventually rifting North America, though that process will take millions of years to complete. The Hocking Hills of Ohio feature caves, waterfalls, and rock shelters carved from Blackhand sandstone, a formation deposited 350 million years ago in ancient river deltas. The sandstone is relatively soft and porous, allowing water to seep through it. Where the sandstone sits atop impermeable shale layers, water flows along the contact, gradually eroding the sandstone from below and creating recesses and caves. Freeze-thaw cycles contribute. Water seeping into the rock freezes in winter, expands, breaks off chunks, gradually enlarging existing openings. The most dramatic features form where streams flow over the sandstone cliffs, creating waterfalls that gradually erode plunge pools and undercut the cliff face, forming caves behind the falling water. Old Man's Cave, the region's most famous feature, is a large recess carved this way, deep enough to shelter travelers, including a hermit who lived there in the 19th century and gave the cave its name. The sandstone's layering creates ledges and overhangs, places where harder layers resist erosion while softer zones are removed. The Hocking Hills demonstrate how even modest waterfalls and seeps can carve dramatic features given enough time, how the combination of soluble rock, impermeable layers, and freeze-thaw cycles creates landscape of surprising complexity. The region's gorges and caves continue forming today, water still seeping, frost still wedging, each winter adding tiny increments to the slow excavation of stone. Mount Rainier in Washington is considered one of the world's most dangerous volcanoes, not primarily for eruption risk, though it is an active volcano that last erupted in the mid-1800s, but for the potential of lahars, volcanic mud flows that could reach populated areas within hours. The mountain hosts the largest glacier system in the contiguous United States, with 25 named glaciers covering 35 square miles of the volcano's flanks. If the volcano erupts, or even if geothermal heat increases beneath the summit, melting this ice rapidly would create massive lahars, mixtures of water, rock, and debris that flow with the consistency of wet concrete and the speed of floodwater. Historical lahars from Rainier have reached the Puget Sound lowlands, traveling over 50 miles and inundating areas now occupied by cities and suburbs. The Osceola mudflow, 5,700 years ago, deposited material up to 70 feet deep across the present site of Kent, Washington. Modern hazard maps show lahar paths would follow river valleys, the Puyallup, White, Nisqually, and Cowlitz drainages, all of which host significant populations. The mountain is monitored continuously for signs of increased seismic activity or ground deformation that might indicate magma movement. The danger lies in the combination of active volcanism, extensive glaciation, and proximity to major population centers, a convergence that makes Rainier uniquely hazardous among Cascade volcanoes. The La Brea tar pits in Los Angeles have trapped and preserved over 3.5 million specimens from the last ice age, creating an extraordinary fossil assemblage concentrated in asphalt seeps that still bubble to the surface in Hancock Park. The asphalt comes from petroleum reservoirs deep underground. Oil that migrates upward through porous rock, seeps to the surface, and loses its volatile components through evaporation, leaving behind sticky tar. Animals coming to drink from pools of water floating on the tar would become mired, unable to escape. Predators and scavengers attracted to trapped animals would themselves become stuck. The tar preserved soft tissues better than normal fossilization, sometimes retaining DNA, pollen, plant material, details usually lost. The fauna preserved represents late Pleistocene California: saber-toothed cats, dire wolves, mammoths, giant ground sloths, camels, horses, a now extinct ecosystem. Notably, predators vastly outnumber prey in the assemblage, reflecting how carnivores were disproportionately attracted to trapped animals. Excavation continues today. Paleontologists still extract fossils from the asphalt, still discover new specimens, still learn about Ice Age ecosystems from this concentrated deposit. The tar pits represent an unusual taphonomic situation where the preserving medium is still active, where asphalt continues seeping, where modern animals occasionally still become trapped, where the process that created the fossil deposit operates unchanged across 40,000 years. Narragansett Bay in Rhode Island occupies a valley carved by glaciers advancing southward during the Pleistocene, their weight and movement gouging the bedrock and creating a depression that later filled with seawater as ice melted and sea level rose. The bay extends 30 miles north from the Atlantic, reaching depths of 180 feet in places, deeper than the surrounding ocean floor in some locations, indicating significant glacial scouring. The valley was originally carved by the primordial Narragansett River, but glacial ice deepened and widened it substantially. When the last ice age ended and glaciers retreated 15,000 years ago, meltwater initially drained through the valley, keeping it above sea level. But as the massive continental ice sheets melted, global sea level rose, eventually flooding the valley and creating the drowned river valley that is Narragansett Bay. The bay's islands are high points of bedrock that remained above water as the valley flooded. Narragansett Bay is technically an estuary, a place where fresh water from rivers mixes with salt water from the ocean, creating gradient conditions that support diverse marine life. The bay's configuration reflects its glacial origin. Elongated north-south following the direction of ice flow, irregular shoreline where glaciers plucked rock unevenly, and numerous islands representing resistant rock that wasn't as deeply eroded. The bay demonstrates how glaciation creates the preconditions for coastal geography, how Ice Age valleys become modern harbors when sea level rises. The Watchung Mountains of New Jersey form 3 parallel ridges of basalt that are not actually mountains in the usual sense, but rather ancient lava flows, tilted and eroded. 200 million years ago, the supercontinent Pangaea began breaking apart, rifting along what would become the Atlantic Ocean. As the crust stretched and thinned, magma welled up from the mantle, erupting through fissures and spreading across the landscape in broad, fluid flows. These eruptions occurred episodically, creating 3 distinct lava layers separated by sedimentary rocks deposited during quiet periods between eruptions. The basalt flows originally were horizontal, but as the Atlantic opened and the region's crust adjusted, the rock layers tilted westward. Erosion then carved this tilted landscape, removing softer sedimentary rocks preferentially while harder basalt resisted, creating ridges where the lava flows outcrop. The Watchung ridges parallel the coast, aligned with the rift system that created them, preserving a record of Pangaea's breakup. Between the ridges lie valleys carved in softer rocks, creating a distinctive ridge and valley topography. The basalt itself is fine-grained and dark, sometimes containing vesicles where gas bubbles were trapped as the lava cooled. The Watchungs represent a moment of continental reorganization preserved in stone, ridges created by ancient volcanism now forming prominent features in New Jersey's landscape, resistant rock standing above its softer neighbors. Yosemite's Half Dome appears as if a massive granite dome was sliced vertically in half, but this dramatic appearance results not from a single catastrophic event, but from gradual exfoliation, the process where sheets of granite peel away along curved joints that parallel the rock's surface. The granite crystallized deep underground as a large batholith 80 million years ago. As erosion removed overlying rock, the granite was gradually exposed and pressure on it decreased. This pressure release allowed the granite to expand slightly, and expansion created fractures roughly parallel to the surface. These fractures, called exfoliation joints, are more closely spaced near the surface and become wider apart deeper in the rock. Over time, sheets of granite bounded by these joints spall off, sometimes thin flakes, sometimes slabs several feet thick. Half Dome's appearance suggests it lost its northwest face suddenly, but evidence shows the face was carved by gradial exfoliation combined with glacial activity. During ice ages, a glacier flowed through Tenaya Canyon and likely plucked away already loosened sheets of granite from the face, steepening it. The southeast side, unaffected by major glacial erosion, retains its dome shape. The distinction between the rounded back and sheer face makes Half Dome distinctive, but both sides formed through the same exfoliation process operating at different rates in different locations. The dome continues shedding rock. Large exfoliation events occur periodically, sometimes triggered by weather changes, frost wedging, or earthquakes, each one representing another moment in the slow unmaking of this granite landmark. Bryce Canyon in Utah contains thousands of hoodoos, tall, thin spires of rock carved by frost, weathering in a landscape that experiences freeze-thaw cycles over 200 times per year. The canyon is actually an amphitheater carved into the eastern edge of the Ponsogunt Plateau, a series of horseshoe-shaped bowls eroded from Clarin Formation limestone. The rock formed 56 million years ago in an ancient lake system, with iron and manganese creating the distinctive pink, orange, and red colors visible in the formations. Frost weathering is remarkably effective here. Water seeps into cracks in the rock during the day, freezes at night when temperatures drop, expands by roughly 9% upon freezing, and wedges the rock apart. This cycle repeats night after night, winter after winter, slowly fragmenting the limestone along vertical joints. The hoodoos form where harder caprock protects softer underlying layers, creating pillars that resist erosion until their caps finally fall away. Each hoodoo is temporary, gradually being reduced by the same frost action that created it, even as new hoodoos form from the cliff face behind them. The landscape is self-renewing in a sense. The amphitheater grows backward into the plateau while new spires develop at its edge. Walk the trails below the rim, and you walk among thousands of these formations, each in a different stage of development or decay, creating a stone forest that demonstrates geology at a scale and pace almost comprehensible to human observation. Louisiana's coastal wetlands are subsiding and disappearing at an alarming rate, losing roughly 1 football field every 100 minutes as sediment compaction, sea level rise, and reduced Mississippi River sediment delivery combine to reshape the state. The land itself is young in geological terms, built from Mississippi River sediment over the past 7,000 years. But the process that built this land, seasonal flooding depositing fresh sediment, has been interrupted by levees that confine the river and prevent it from spreading sediment across its floodplain. Meanwhile, the existing land compacts under its own weight. Organic material in the wetlands decomposes and shrinks, and subsurface fluid extraction causes the ground to sink. The Gulf of Mexico, rising incrementally as global climate warms, advances inland as the land drops. Saltwater intrusion killing freshwater marshes, waves eroding what was once protected wetland. Aerial photographs from different decades show the dramatic change. Solid land becoming open water, protective barrier islands fragmenting and disappearing, coastline retreating miles inland. The loss represents not just geography, but also habitat, storm protection, fisheries, and cultural landscapes. Louisiana's coast demonstrates that geological processes don't always operate on timescales of millions of years. That dramatic landscape change can occur within human lifetimes when multiple factors align: natural subsidence, human engineering, climate change, all accelerating the transformation of land to water. The Palisades along the Hudson River in New Jersey and New York form a dramatic cliff rising 300 feet, composed of diabase that crystallized as a horizontal sheet of magma intruding between rock layers 200 million years ago. The diabase formed during the same rifting event that created the Watchung Ridges, Pangaea breaking apart, magma rising through the extending crust. But unlike lava flows that erupted onto the surface, the Palisades magma squeezed horizontally between sedimentary layers and cooled underground, forming what's called a sill. The slow cooling created coarse-grained diabase with visible crystals of feldspar and pyroxene. Over millions of years, erosion removed overlying rocks, eventually exposing the hard diabase. Then the region tilted slightly, raising the western edge of the sill, while the eastern edge remained lower. The Hudson River, flowing through a valley carved by glaciers, encountered this tilted sill and eroded preferentially along its eastern edge, creating the cliff face visible today. The Palisades present an imposing wall above the river, columnar jointing in places, creating vertical fractures that make the cliff appear constructed rather than natural. Quarrying in the late 19th and early 20th centuries removed sections of the Palisades for construction material, prompting conservation efforts that eventually protected the formation. The cliffs stand now as both geological feature and historical artifact, stone intruded 200 million years ago, exposed by erosion, threatened by industry, preserved by advocacy, a landscape whose history includes both geological and human chapters. Meteor Crater in northern Arizona spans nearly 1 mile across and 550 feet deep, created 50,000 years ago when a nickel-iron meteorite 150 feet wide struck at 26,000 miles per hour. The impact lasted perhaps 10 seconds. The meteorite encountered Earth's atmosphere, flashed through it almost unslowed by air resistance, struck the ground with kinetic energy equivalent to a 10-megaton nuclear weapon. The meteorite vaporized instantly, the explosion excavating 175 million tons of rock, ejecting it upward and outward, creating a crater in moments. The rim rose higher than the surrounding plain, built from overturned rock layers pushed up by the impact. Shocked quartz with distinctive microscopic fractures created by extreme pressure, litters the area, evidence of the forces involved. Scattered meteorite fragments, mostly fist-sized or smaller, are occasionally found near the crater, remnants of the impactor that didn't completely vaporize. The crater is remarkably well preserved because of the arid climate and its relative youth. Erosion hasn't had time to soften its features. The floor has partially filled with sediment, and vegetation grows on the rim and walls. But the crater's form remains clear, its origin unmistakable. Meteor Crater served as a training site for Apollo astronauts and continues as a focus for impact geology research. It demonstrates that Earth remains vulnerable to cosmic collision, that forces from beyond our planet occasionally reshape our surface with violence impossible to imagine until you stand at the rim looking across the scar left by a rock from space. The Shawnee Hills in southern Illinois represent ancient mountains worn nearly flat. Low ridges containing coal seams and fossils from when the area was a tropical swamp forest 300 million years ago. The hills were once significantly higher, part of a mountain system raised during continental collisions. Erosion has been working on them ever since, reducing what were peaks into gentle hills, removing mile after mile of vertical rock. What remains are the roots of those mountains, resistant sandstone forming the ridges, while softer shale eroded into valleys. The coal seams tell a different story. They represent the swamp forests that grew here during the Carboniferous period, vast wetlands where giant ferns and primitive trees accumulated as peat when they died. Burial and compression over millions of years transformed the peat into coal, creating economically important deposits that were mined extensively in the 20th century. The forests that grew here knew a world radically different from today's. Oxygen levels were higher, carbon dioxide levels were higher. The climate was warm and humid even at these temperate latitudes. Giant arthropods, some with wingspans exceeding 2 feet, flew through these forests. Amphibians the size of small cars occupied the swamps. The Shawnee Hills preserve evidence of that lost world in their rock layers and fossils, reminders that Illinois was once mountainous, then tropical, and that landscapes cycle through drastically different states across geological time. The Salton Trough in southeastern California sits 227 feet below sea level and continues sinking along the southern extension of the San Andreas Fault System, making it one of the lowest points in North America. The trough is a pull-apart basin formed where the San Andreas and related faults create a zone of crustal stretching. As tectonic blocks slide past each other, gaps open between them, creating depressions that drop below sea level. The Imperial Valley, agriculturally productive despite its desert location, occupies this trough, its fertility sustained by Colorado River water delivered by canal. But the geological reality is that the trough is gradually deepening through ongoing tectonic activity. The region experiences frequent small earthquakes as the crust adjusts and faults slip. The Salton Sea occupies the lowest part of the trough, having formed accidentally, but occupying a depression that has held water many times before in the geological past. The trough continues southward into Mexico, where it connects with the Gulf of California, essentially an oceanic rift. The Salton Trough represents the northernmost extension of this rifting, a zone where the Pacific Plate and North American Plate are not just sliding past each other, but pulling apart, creating subsidence. Eventually, millions of years from now, continued rifting may connect the trough fully with the Gulf, turning it into a narrow sea. For now, it remains below sea level, but above seawater, a depression sustained by tectonics, filled intermittently with lake water, always subject to the forces pulling it downward. Mount Washington in New Hampshire records some of Earth's most extreme weather, despite standing just 6,288 feet high, with a recorded wind gust of 231 miles per hour in 1934 that remained the world record for surface wind speed for decades. The mountain's weather results from its position where three major storm tracks converge and its abrupt rise above surrounding terrain. Storm systems moving up the east coast, systems coming across the Great Lakes, and systems descending from Canada all meet in the White Mountains. Mount Washington, being the highest peak, bears the full force of these converging weather patterns with no intervening terrain to slow the winds. The mountain creates its own weather to some extent. Air forced upward over the summit cools rapidly, creating clouds even when surrounding areas are clear. Temperature inversions trap cold air near the summit. Rime ice builds on the summit structures during winter, creating bizarre formations as supercooled fog freezes instantly on contact with any surface. The weather observatory on the summit has been continuously staffed since 1932, recording conditions that regularly include hurricane-force winds, temperatures far below zero, and visibility measured in feet. The mountain demonstrates that extreme weather doesn't require extreme elevation. Position and topography matter more than height. Washington experiences alpine conditions despite being shorter than many Rocky Mountain peaks that see far gentler weather, proving that latitude, exposure, and the convergence of storm tracks create environments as harsh as much higher elevations. The Guadalupe Mountains in West Texas expose an ancient barrier reef from the Permian period, 265 million years ago, when a tropical sea covered the region. The reef was similar to modern coral reefs, but built primarily by algae, sponges, and bryozoans, rather than coral. The reef grew along the edge of a deep ocean basin, rising from depths of several thousand feet to just below sea level. For millions of years, the reef-building organisms deposited calcium carbonate, extending the reef seaward and upward. When sea level dropped and climate changed, the reef died and was buried under sediment. Then, much more recently in geological time, just 10 million years ago, tectonic forces uplifted the entire region, raising the ancient reef to over 8,000 feet above sea level. Erosion has since exposed the reef structure in remarkable detail. El Capitan, the sheer cliff at the south end of the Guadalupe Range, consists entirely of reef limestone, the front face of the ancient barrier. You can see the massive limestone beds that formed the reef core, can trace where the back reef lagoon was, can identify the basin deposits that accumulated in deep water beyond the reef. The Guadalupes present one of the best exposed fossil reefs in the world, now frozen in stone at high elevation, allowing geologists to study ancient reef ecology and structure in a way rarely possible. The mountains demonstrate how radically geography can change. Seafloor becoming mountaintop, tropical ocean becoming arid desert, all through the patient work of tectonic forces operating across spans of time that turn seas into stone and raise stone into sky. The Loess Hills along the Missouri River in western Iowa consist of wind-blown silt up to 200 feet thick, deposited during and after the last ice age, when glacial meltwater created vast outwash plains. As glaciers melted, rivers carried enormous volumes of sediment. Rock flour ground fine by glacial movement, silt and clay transported downstream. These sediments accumulated on floodplains where, when the rivers dropped during dry seasons, the fine material dried out. Strong westerly winds then picked up the lightest particles, primarily silt-sized grains, and carried them eastward. Where the wind encountered obstacles or slowed, the silt settled out, accumulating over thousands of years into hills that rise sharply above the Missouri River Valley. The Loess is unconsolidated, held together primarily by root systems, highly erodible when vegetation is removed. Vertical faces can be cut in Loess. It maintains near vertical angles because of slight cohesion between particles, but erodes rapidly when exposed. The Loess Hills create distinctive topography, knife-edge ridges and steep slopes more dramatic than typical Iowa landscape. Similar Loess deposits exist in China, where wind-blown silt from the Gobi Desert created the Loess Plateau. But Iowa's deposits are among the most extensive in North America. The hills represent an unusual preservation of glacial age sediment, material that was ground by ice, transported by water, moved by wind, and deposited in forms that have persisted for 15,000 years, creating terrain that seems incongruous in the Midwest, but makes perfect sense when viewed through the lens of Pleistocene climate. The Aleutian Islands form an 1,100-mile volcanic arc where the Pacific Plate subducts beneath Alaska, creating one of the most seismically and volcanically active regions on Earth, with 52 historically active volcanoes. The islands are the visible portions of submarine volcanoes built over millions of years by magma generated as the Pacific Plate descends into the mantle. Water carried down with the subducting plate lowers the melting point of mantle rock, creating magma that rises and erupts, building volcanic mountains. The arc curves gracefully from the Alaska Peninsula westward toward Russia, mirroring the curved boundary where the Pacific Plate bends downward. The islands are young in geological terms, most less than 2 million years old, constantly being reshaped by eruptions. Some volcanoes grow, others collapse in caldera-forming eruptions. New islands occasionally emerge from the sea. The region generates powerful earthquakes along the subduction zone. The magnitude 9.2 earthquake in 1964 originated in this system, causing tsunamis across the Pacific. The Aleutians represent one of Earth's fundamental geological processes. Oceanic crust created at mid-ocean ridges eventually returns to the mantle at subduction zones, recycling sea floor into the planet's interior. The islands mark where this process occurs, where old ocean crust descends, where volcanoes manifest the connection between surface and deep interior, where the Pacific Ring of Fire demonstrates that plate tectonics remains vigorously active, reshaping the planet's surface through forces operating between crust and mantle. The Green Mountains of Vermont consist primarily of metamorphic rocks transformed by heat and pressure, when ancient continents collided 450 million years ago during the formation of the Appalachians. The rocks began as sediments, sandstone, shale, limestone, deposited in an ocean basin. When continents converged, the oceanic crust was forced downward, and the sediments that had accumulated on it were scraped off, crumpled, and thrust up onto the continental margin. The collision generated intense heat and pressure, transforming the sediments into metamorphic rocks: schist, gneiss, marble. Some rocks were pushed so deep they partially melted, creating migmatites, mixed rocks with both metamorphic and igneous characteristics. The mountains themselves have been eroding for hundreds of millions of years, reduced from peaks that once rivaled the Himalayas to the rounded summits of today. But the metamorphic rocks record the intensity of mountain building. Minerals aligned in bands showing the direction of pressure. Crystals grown under extreme conditions. Rocks that flowed like plastic under the forces of collision. Vermont's marble comes from limestone transformed by this process, now quarried and used in buildings and monuments. The Green Mountains represent Appalachian geology in profile: ancient collision, intense metamorphism, prolonged erosion, all recorded in rocks that began as seafloor sediment and became mountain ranges through the collision of continents. The Gulf of Mexico's dead zone covers up to 8,000 square miles each summer when nutrients from the Mississippi River watershed stimulate massive algae blooms that deplete oxygen when they decay. The process is fundamentally geological. Rivers carry dissolved nutrients eroded from soil and rock throughout the drainage basin, concentrating them and delivering them to the Gulf. But human agriculture has amplified the natural process. Fertilizers applied to fields throughout the Midwest, washing into streams, and eventually reaching the Gulf in quantities far exceeding natural levels. The excess nutrients cause explosive algae growth. When the algae die and sink, bacteria decompose them, consuming oxygen in the process. The Gulf's bottom waters become hypoxic, oxygen depleted, to the point where fish and other mobile organisms must leave or die. Bottom-dwelling organisms with limited mobility experience mass mortality. The dead zone forms predictably each summer when river flow peaks with spring runoff, and stratification keeps oxygen-poor bottom water separate from oxygenated surface water. The phenomenon demonstrates how geological processes, weathering, erosion, sediment transport, nutrient delivery, interact with biological systems to shape marine environments. And it shows how human activity can amplify natural geological cycles, accelerating nutrient delivery beyond what ecosystems evolved to handle, creating conditions where natural processes become problematic at scales and intensities that disrupt the biological systems dependent on stable conditions. Delaware sits entirely on the Atlantic coastal plain, composed of sediments deposited over the past 100 million years by ancient seas and rivers, with no natural rock outcrops and the lowest average elevation of any state. The state's geology is entirely sedimentary, layers of sand, clay, silt, and gravel that accumulated as sea level fluctuated and shorelines moved across the region. When sea level was high, marine sediments accumulated. When sea level dropped, rivers flowing across the exposed plain deposited terrestrial sediments. The layers stack in sequence, each representing a different episode in the region's history. None of the rock is consolidated enough to form outcrops in the typical sense. It's all loose or semi-consolidated sediment. Groundwater is abundant, stored in porous sand layers sandwiched between impermeable clay beds, creating aquifers that supply much of the state's water. The flat terrain reflects the sedimentary nature. Coastal plains lack the topographic relief associated with harder, older rocks. Delaware's highest point is just 448 feet above sea level, and much of the state sits within feet of sea level. The state demonstrates that not all landscapes involve mountains and valleys carved in ancient bedrock. Some regions are entirely young sediment, still accumulating, still being shaped by ongoing deposition and erosion, still developing their geological character. Delaware represents the edge of the continent in both geographic and geological terms, where land meets ocean, where the oldest rocks are measured in millions rather than billions of years, where the substrate remains loose and mobile rather than consolidated into solid stone. The crazy mountains of Montana rise as isolated peaks formed by volcanic intrusions 60 to 75 million years ago, creating laccolith formations where magma pushed up overlying rock layers into dome shapes without reaching the surface. Laccoliths form when magma intrudes between rock layers with enough force to lift the overlying beds, but not enough to break through to the surface. The magma spreads horizontally, creating a lens-shaped intrusion that domes the rocks above it. When the magma cooled, it formed igneous rock, primarily diorite and related types, more resistant than the sedimentary rocks it intruded. Over millions of years, erosion removed the softer sedimentary rocks, gradually exposing the harder igneous cores. The crazy mountains now stand as erosional remnants, the resistant cores of ancient laccoliths surrounded by lower terrain where softer rocks have been removed. The range is isolated, rising dramatically from the surrounding plains without the gradual approach typical of most mountain ranges. The peaks are rugged and glacially carved, ice ages having modified the igneous rock into sharp summits and U-shaped valleys. The crazies demonstrate that mountains can form through various processes. Not all require massive continental collisions or hotspot volcanism. Some result simply from magma pushing upward, doming overlying rocks, and then being revealed by the patient removal of everything surrounding them. The mountain's name supposedly comes from a woman who went mad after her family was killed by Native Americans nearby. But the geological story is equally dramatic in its own way. Mountains built by intrusion, revealed by erosion, standing as monuments to the forces that shape landscapes from below. The Berkshire Hills in western Massachusetts contain marble deposits metamorphosed from limestone when continental collision created intense heat and pressure 450 million years ago. The limestone began as shallow marine sediments, accumulating layer by layer on an ancient seafloor. When continents collided during the formation of the Appalachians, these sediments were buried deeply, subjected to temperatures and pressures that recrystallized the calcium carbonate into marble. The marble is now exposed in quarries and natural outcrops throughout the Berkshires, its white to gray color and crystalline texture distinctive. Some marble contains bands of color where impurities in the original limestone created patterns preserved through metamorphism. The stone has been quarried for over 2 centuries, used in buildings, monuments, and sculptures. The marble also appears in stone walls throughout New England, where farmers clearing fields stacked the stones they encountered, inadvertently creating fences from metamorphosed seafloor. The Berkshire Hills themselves are rounded, gentle mountains heavily forested, showing the effects of hundreds of millions of years of erosion since the Appalachians formed. Glaciers modified the landscape during the ice ages, smoothing valleys and depositing erratic boulders. What remains is terrain that appears peaceful and stable, but records violent geological history, ocean closure, continental collision, rock transformation under extreme conditions, mountain building, and subsequent erosion, all preserved in the marble that forms these ancient hills. The channeled scablands floods moved water at 10 times the combined flow of all rivers on Earth today, creating geological features at scales difficult to comprehend. 400-foot waterfalls that have since vanished, left behind dry cataracts, vertical cliffs where water once thundered over the edge. Giant ripples in gravel bars measure 30 feet high and 300 feet from crest to crest, looking like sand ripples, but at the scale of buildings. Massive, erratic boulders, some weighing hundreds of tons, were carried tens of miles and deposited randomly across the landscape. The floods stripped topsoil down to bedrock across hundreds of square miles, creating the scabland appearance, bare basalt with only scattered soil in protected pockets. Temporary lakes formed where floodwater pooled behind natural barriers, then drained catastrophically when water levels rose high enough to overtop or breach the barriers. The floods occurred repeatedly, at least 40 times over several thousand years as Lake Missoula formed and failed, so the landscape records multiple episodes of catastrophic erosion. Each flood enlarged existing features, carved new channels, moved more sediment. What makes the scablands remarkable is the preservation of features at catastrophic scale. Normal rivers working over millions of years create their own distinctive landforms, but these floods created features in days that would normally require eons, operating at intensities that demonstrate how much work moving water can accomplish when volumes and velocities exceed normal experience. Cathedral Caverns in Alabama contains one of the world's largest cave entrances at 126 feet wide and 25 feet high, leading to massive chambers carved from limestone by slightly acidic groundwater over millions of years. The entrance is so large, it was used as a dance hall in the 1950s before becoming a state park. Inside, the caverns extend through formations typical of limestone caves, but at unusual scale. A stalagmite nicknamed Goliath stands 45 feet tall and has been growing for millions of years as mineral-rich water drips from above, leaving behind calcium carbonate deposits. A frozen waterfall of flowstone covers one wall, formed where water sheeted across the cave surface, depositing minerals in layers that built up into a cascade-like formation. The caverns formed as water percolated through the limestone, dissolving pathways that gradually enlarged into passages and rooms. The big room covers 3 acres, the ceiling high enough to feel like open air despite being underground. The temperature remains constant at 60 degrees year-round, the humidity high, conditions that allow formations to continue growing. Cathedral Caverns demonstrates that caves can develop enormous chambers when conditions favor dissolution and when the limestone remains stable enough not to collapse. The entrance size likely resulted from preferential erosion along a zone of weakness, perhaps a fault or a contact between different rock layers that allowed surface erosion to connect with underground passages. The Snake River Canyon in Idaho was carved when the Snake River captured the drainage of ancient Lake Idaho roughly 2 million years ago, causing rapid downcutting through basalt layers and creating a gorge over 500 feet deep in places. Before the river captured the lake's drainage, water flowed differently across the region. When the snake established its current path, suddenly, much higher volumes of water flowed through what had been a smaller stream. The increased flow gave the river tremendous erosive power, allowing it to cut downward rapidly through the layered basalt. The canyon walls expose multiple lava flows stacked like pages in a book, each flow representing a separate eruption from the volcanic fields that built the Snake River Plain. Some flows show columnar jointing, where cooling magma fractured into hexagonal columns. Others display ropey peiho-ho textures. The river continues cutting downward today, though more slowly as it approaches base level. Shoshone Falls, upstream from the canyon, demonstrates the river's power. A waterfall higher than Niagara, formed where the river flows over resistant basalt. The canyon represents what happens when drainage patterns reorganize, when a river suddenly captures a new watershed, when flow volumes increase dramatically and erosive power multiplies. the landscape adjusts rapidly in geological terms, cutting canyons in hundreds of thousands of years that look like they should have taken millions, showing that river erosion operates at variable rates depending on flow conditions. Connecticut's Central Valley is a rift basin formed 200 million years ago when Pangaea began breaking apart, filled with sedimentary rock and basalt lava flows that now create distinctive trap rock ridges across the state. The valley formed as the crust stretched and faulted, creating a down-dropped block between parallel faults. Rivers flowing into this depression deposited thick sequences of sediment, sandstone and shale known as the Newark supergroup. Periodically, the crust would fracture more deeply, allowing basaltic magma to reach the surface and erupt, creating lava flows that spread across the valley floor. These eruptions happened episodically, so sedimentary layers alternate with basalt flows, creating a striped geology visible in cliff exposures. The basalt, being harder and more resistant than the sedimentary rocks, now stands as ridges where softer rocks have eroded away. These trap rock ridges, Talcott Mountain, Hanging Hills, and others, are distinctive features of Connecticut's geography, rising sharply above the surrounding landscape. The valley itself represents an aborted rift, a place where the continent started to split but then stopped, leaving a failed rift preserved in rock. Had the rifting continued, the Atlantic might have opened here, and Connecticut might have been on the edge of a different ocean. Instead, the rift failed, the Atlantic opened farther east, and Connecticut's Central Valley remains as evidence of tectonic processes that began but didn't complete their intended transformation. The Superstition Mountains of Arizona contain legends of lost gold mines, but their actual geological treasure lies in the volcanic rocks, compressed layers of tuff, ash, and lava flows from eruptions 18 to 29 million years ago that built a massive volcanic field now carved into dramatic peaks. The volcanism occurred during the basin and range extension, when the crust stretched and thinned, allowing magma to reach the surface. Multiple volcanic centers erupted explosively, ejecting ash that settled in thick layers. Some eruptions produced pyroclastic flows, hot clouds of gas and ash that raced across the landscape, accumulating as welded tuff when temperatures were high enough to fuse the ash particles together. Lava flows added to the sequence, creating the complex stratigraphy visible in cliff faces. After the volcanism ceased, erosion began carving the volcanic field into mountains, creating the rugged topography that characterizes the superstitions today. The rock is relatively soft, eroding readily, but also capable of standing in dramatic cliffs and spires. The mountain's name allegedly comes from Apache legends, and the Lost Dutchman's Mine has attracted treasure seekers for over a century. But the real treasure is the geological record, layers that document millions of years of volcanic activity, that reveal how explosive eruptions build volcanic fields through repeated episodes, that show how erosion transforms flat volcanic plains into mountainous terrain. The superstitions stand as monuments to fire and time, volcanic stone carved by water and wind into forms that inspired legends even as they record geological processes.